Without this unassuming rock, often mistaken for ordinary dark pebbles or heavy chunks of granite, modern electronics would instantly collapse into a pile of useless plastic and silicon. Tin ore, or more precisely its primary mineral, Cassiterite, is the hidden foundation holding up our entire digital world. When we talk about high-tech, we name-drop gold or complex semiconductors, but this is the invisible glue binding billions of microscopic components into a single working system. Tin's journey begins deep in the planet's crust, where for millions of years, metal-rich solutions seeped into fractures in the earth, forming deposits that today drive the pace of human progress. Cassiterite, often called tinstone, has an incredible density and a distinctive diamond-like luster when fractured, though on the outside, it can look like ordinary brown or black rock. Mining this ore demands massive effort and specialized knowledge. The world's major reserves are concentrated in what's called the Tin Belt, stretching through Southeast Asia, China, Latin America, and Africa. The scale of extraction is staggering in its variety, from colossal open-pit mines and underground shafts to dredging operations on the ocean shelf. For example, off the coast of Indonesia, giant floating dredge factories pull up thousands of tons of tin-bearing sand from the seafloor, sifting it through complex filter systems to separate out the heavy ore particles. The process of transforming rock into pure metal is long and exhausting. Since tin content in ore is now low, the rock first undergoes multi-stage enrichment. It's crushed, washed, and separated using gravity methods that exploit Cassiterite's high specific gravity. After obtaining the concentrate, the smelting stage begins in a furnace at around 2,200 degrees Fahrenheit. Here, under the influence of reducing agents, tin separates from oxygen and other impurities, transforming into a liquid silvery metal. But for the electronics industry's needs, this purity isn't enough. The metal goes through a series of refining processes to eliminate the tiniest traces of iron, copper, arsenic, or antimony. Only after this does it become the material we see in the form of solder. Solder. That's the main use for tin in the modern world. It's not just some auxiliary material. It's a critically important component of any electronic device. Previously, soldering used an alloy of tin with lead, but due to environmental requirements and health safety concerns, the world switched to lead-free technologies. Today, the latest circuit boards are joined using alloys where tin makes up 95 or even 99%. Every smartphone, laptop, control unit in cars, or satellite onboard computer contains several thousand soldered connections. Without tin's ability to wet the surfaces of other metals and create reliable electrical contact at low temperatures, mass production of electronics would be impossible. Factories that produce modern electronics operate with incredible precision, and that's where a key tool comes into play. In surface mount assembly shops, specialized machines deposit solder paste through stencils onto circuit boards with accuracy down to the micron. Then the board passes through reflow ovens, where the paste transforms into solid metallic connections. It's an automated process where every second and every milligram of metal matters. If the tin contains even minor foreign impurities, it can lead to microcracks or tin whiskers, thin thread-like crystals that grow from the solder and can cause short circuits. That's exactly why quality requirements for tin ore and purification methods keep getting stricter. The impact of tin on urban development and global energy is hard to overstate. Sure, we don't build house frames from this stuff, but it's in every lighting control system, every elevator, every safety sensor. The growth of smart cities relies entirely on billions of sensors and controllers, each one held together by tin solder. This makes it a critical strategic resource, with entire regions shaping their economic policy around the battle for control over its deposits. Countries with major Cassiterite reserves become key players in the high-tech supply chain. But tin ore extraction comes with serious challenges. Deep open pits and seabed dredging reshape ecosystems, demanding strict reclamation standards. Responsible companies try to minimize environmental impact by restoring forests and cleaning water used in the refinement process. At the same time, recycling is playing a bigger role. Tin is a metal that can be cycled back infinitely. Recycling old circuit boards keeps the metal's high purity with way less energy than mining it from ore. This creates a closed-loop economy, where yesterday's shattered screen becomes the source material for a new device. Interesting fact, tin's been used for millennia. When it combined with copper to create bronze, it gave an entire era of human history its name. Back then, tin was hunted down as aggressively as we hunt for oil or gas today. But while ancient people made swords and cookware with it, today it's become a tool for transmitting information. That's the evolution of this metal's role. From the brute force of bronze weapons to the refined precision of a silicon chip, where tin provides the pathway for electrons to flow. The stone once prized for its ability to make copper hard is now valued for its malleability and conductivity in the micro world. Technological progress demands ever-increasing quantities of this metal. The growth of renewable energy, solar panels, and electric vehicles creates additional demand. Each photovoltaic panel requires tin connections to harvest the sun's energy. Electric vehicles contain significantly more electronic components than internal combustion engine cars, making this element essential in the fight for climate neutrality. Thus, ancient Cassiterite becomes fuel for the green revolution. It's crucial to understand that tin deposits are distributed extremely unevenly across the planet. This creates certain risks for global production stability. Any disruptions in ore supply from major mining regions instantly impact consumer technology worldwide. This pushes scientists to search for new methods of enriching even low-grade ores, as well as developing technology for extraction from deeper horizons. Every foot of new mine shaft or every mile of surveyed deposit is a guarantee that factories keep producing new devices, and the planet's digital network continues to expand. The transformation of tin from mountain rock to solder on a circuit board is an example of how humanity has learned to harness the special properties of materials to achieve remarkable results. It's about tin's ability to be the connecting link. When we look at a chunk of tin ore, we see not just a mineral, but the potential for millions of conversations, terabytes of transmitted data, and the operation of complex mechanisms that ensure our comfort. Tin remains a humble yet irreplaceable hero of the industrial stage, working where no one sees it, at the very heart of machines. Production chains that begin in quarries and end in the clean rooms of high-tech factories are testament to our global interdependence. Tin isn't just a detail on a circuit board. It's the backbone of economies across continents. The continuous flow of ore, concentrate, and finished metal is the circulatory system of industry. Every ton of Cassiterite pulled from the earth passes through the hands of thousands of specialists before becoming part of our global information infrastructure. And as we move toward even greater automation and digitization, the role of this stone will only grow, proving that great achievements often start with very small but critically important details. So, tin ore is the real key to modernity. It teaches us to value resources that seem invisible, but without them, the world we know would cease to exist. This is a story about how nature gives us materials, and human ingenuity finds the perfect use for them, transforming heavy ore into the lightness of wireless communication and the speed of data processing. Every grain of Cassiterite carries its contribution to global development, remaining an eternal reminder that high technology has its roots in the work of the earth, a stone-born origin. From dark depths to gleaming device cases, the journey of tin is the journey of progress itself. In every second of our lives, there are metals we don't even suspect. Without them, there would be no smartphones, electric cars, or even jet aircraft. And now imagine a place where, in the middle of the desert, under the scorching California sun, the United States creates a strategic resource of the future, without a single pound of Chinese raw materials. Here, at Mountain Pass, they mine 43,000 tons of rare earth metals annually. Rocks that look ordinary are transformed into materials for lasers, engines, and defense systems. But there's something almost no one knows about. And if you watch till the end, you'll understand why this dust from the desert can change the world. Today here, in the dust and heat, MP Materials Company mines 43,000 tons of rare earth concentrate per year, all without a single pound of Chinese raw materials. For a country that for decades depended on imports from China, this is a strategic breakthrough. The main star of this place is basnasite, a mineral that looks like an ordinary stone but contains treasures inside: lanthanum, cerium, neodymium, and praseodymium. These very elements give life to modern magnets, lasers, electric cars, and jet aircraft. Everything begins in the depths of the quarry. Huge excavators and 300-ton trucks carry rock to the crusher. Next comes the flotation process, similar to a magic sieve. Crushed ore is mixed with water and special reagents. All this turns into foam, and basnasite particles float to the surface, while waste settles to the bottom. After flotation, basnasite goes for chemical expertise. In MP Materials laboratories, it's transformed into concentrate, and then into individual elements. This is a complex sequence of extractions and washes, where each metal chooses its own path. Once, this stage was performed in China. Now the United States is gradually building a full production cycle, from ore to finished magnets. Thanks to this, the country has already replaced 80% of its former imports from Asia, and this is just the beginning. It sounds like science fiction, but it's a fact. 2 pounds of cerium can become material for optical lenses of laser systems in military equipment. Other elements, like neodymium, are used in powerful magnets of jet engines and in missile guidance systems. All this means that every ton of ore from Mountain Pass isn't just raw material. It's a piece of American defense independence. The California desert isn't just scorched by the sun. It's politically charged. Mountain Pass is a symbol of a new era where technology and geopolitics merge. Today, American engineers, in hard hats and safety glasses, are literally building their own supply chain of the future, step by step displacing the Chinese monopoly. Just as in the 60s, when the United States first launched a satellite, now they're trying to be first to build an independent rare earth elements industry. And it all starts right here, among the sands, where it was once quiet, but now machines rumble, and the fire of smelting furnaces glows. If you gather all the rare earth elements mined here per year, it's 43,000 tons of concentrate. Outwardly ordinary dust, but actually strategic raw material, more valuable than gold. And if this dust were transformed into finished products, it would power more than 100,000 electric vehicles, those that race without a drop of gasoline thanks to neodymium magnets in motors. The same metals would ensure the operation of hundreds of guidance systems for F-35 fighters, where precision depends on microscopic lasers and sensors. And also, tens of thousands of medical lasers used for eye surgeries or to stop bleeding in military hospitals. The irony is that Mountain Pass isn't a megapolis or a Silicon Valley laboratory, but a patch of land in the middle of the desert. But it's precisely this place that's becoming a PowerPoint again. Every kilogram of cerium mined here is a potential lens for lasers in defense systems. Every gram of neodymium is a piece of an engine for an electric car or satellite. It's worth talking separately about cerium. Cerium isn't just another metal on the list of rare earth elements. It's one of those that sits quietly beneath the surface of technologies, but without it, the modern world would look completely different. Imagine a desert quarry, drilling rigs, machine cries, and dust, and among all this, under sand and stone, hides a complex chemical actor that transforms from an ordinary mineral into a material that affects aircraft, phones, and even medicine. In appearance, an ordinary grayish powder, nothing special. But this is a true alchemist among metals. Without it, there would be no clean glass in telescopes, no shine in smartphones, no precision of lasers, and no cleaner air from automobile exhausts. 1 gram of cerium can do what other materials can't even in hundreds of times larger quantities. Cerium is a true master of transformations. In catalysts, it behaves like a chemical chameleon. It intercepts and releases oxygen, converting harmful gases into harmless ones. In glass, it extinguishes ultraviolet light, makes lenses transparent as crystal. Its oxide polishes phone screens, cameras, optical devices, literally erasing microscopic scratches from surfaces to perfect smoothness. Among workers at the plant, there's a joke. Without cerium, the world wouldn't shine. And there's truth in this. Because when it gets into engineers' hands, everything around starts to shine. Literally. It helps see farther, move faster, burn cleaner, heal more precisely. All this, from desert dust, from a place where heat reaches 110 degrees Fahrenheit, and wind sweeps away traces in a few minutes, as a symbol that even in the driest desert, the future can be born. Mountain Pass was once just a point on the map, the only mine of this type in all of North America. But now it's surrounded by an entire network of structures that transform crude ore into pure elements, ready for the most complex technologies, from electric motors to jet guidance systems. MP Materials Company has built here not just a mine, but a closed-cycle production, something America lost back in the 1990s when all supplies depended on China. After many years of research and investments in hundreds of millions of dollars, new lines operate almost without human participation. All processes are controlled by computers. Sensors measure compound purity, robotic cranes move containers, and special cameras capture every dust particle. Air in laboratories is so sterile that it feels like it's not a desert, but a space station. Everything that comes out of these shops is sent to other factories, which are also being built inside the country. In Texas and Ohio, they're building factories that will manufacture permanent magnets, precisely those that ensure the operation of Tesla electric motors, wind turbines, or fighter guidance systems. Once these magnets were supplied from China almost 100%, but now America plans to completely switch to its own materials by 2030. People who work here say they feel part of something bigger than just production. When they watch as a substance comes out of desert soil that will later turn into part of a satellite or a high-precision laser, it resembles a true miracle. Next to the quarry grow warehouses, laboratories, transport hubs, and on the horizon, also solar panels that power this giant. After the mine closed in 2002, when Chinese companies effectively monopolized the rare earth elements market, only a few dozen workers remained in the Mountain Pass area, maintaining security and basic infrastructure. The nearby settlement declined. Stores closed, roads overgrew with weeds, and local families moved out to look for work. When in 2017, MP Materials Company bought out the assets and launched a modernization program, the situation began to change literally from scratch. Over several years, more than 800 jobs were created at the enterprise itself, not counting hundreds of related ones, in transport, chemical supply, technical service, energy, and even local services. In neighboring towns, cafes reopened, schools received funding, and roads, repairs. Besides direct vacancies, MP Materials launched a professional training program, cooperating with local colleges. Graduates of technical specialties can now do internships right at the modern processing plant, where they learn to work with automated lines, flotators, hydrocyclones, and chemical separation systems. Interestingly, jobs here are very diverse, from geologists, chemical engineers, process operators, to programmers and data analysts who control plant operations through digital panels. Each shift means tens of thousands of parameters read by sensors in real time. In a broader sense, the revival of Mountain Pass has become a symbol of the return of American manufacturing, which for decades was exported abroad. Against the background of political statements about reshoring and strengthening the internal supply chain, this project is often cited as proof that even in the desert, you can create a modern, profitable, and stable industry. Every year, machines are built around the world so massive and powerful that a single one could supply electricity to an entire city, and costs as much as dozens of private jets. But what if I told you that inside this colossal structure, there are parts machined with precision, thinner than a human hair, And that one tiny mistake could cost millions of dollars or even destroy everything. Today we're going inside a place almost no one gets to see, the heart of turbine manufacturing. And trust me, what you're about to see will completely change how you think about engineering, if you stick around till the end. Let's start with the fact that there are two main types of these turbines, and they work on very different principles. First, the steam turbine. You'll find these at nuclear and thermal power plants, on massive tankers and icebreakers. Second, the gas turbine. It's more like a giant jet engine without wings and lives mostly at gas-fired power plants and on some military vessels. Here at the factory they make both types, but we're heading first to the steam ones because they're older, more massive, and look like they were invented 2 centuries ago. Which, actually, they were, but they're still very much around. How a steam turbine works: short and formula-free. There's a boiler that heats water into pressurized steam at anywhere from 800 to 3,000 pounds per square inch. This steam, hot, pressurized, angry, blasts through nozzles onto rotor blades. The blades start spinning. The rotor spins the shaft. The shaft spins a generator or a ship's propeller. The steam cools down, condenses back into water, and returns to the boiler. The cycle is closed. Sounds simple, but for this simple not to explode into pieces and to run for 3 years without major repairs, you need all of this around me. The first shop they take me to is the foundry. This is where every turbine begins. The casing, the outer shell that holds all the internal components under pressure, is cast from alloy steel or cast iron, depending on operating parameters. For steam turbines in large power plants, the casing is cast in 2 or 3 tiers, and each tier is a separate mold. The mass of 1/2 of a casing can reach 60 to 80 tons. The metal is melted in arc furnaces with a capacity of 50 to 150 tons of molten metal, and the temperature there is around 5,000 degrees Fahrenheit. The mold for a large casing is a pit in the floor, 6 to 10 feet deep, lined with refractory clay. The metal is poured through a system of channels, and the entire process of filling one large mold takes 15 to 30 minutes. Then the casting cools, naturally from several days to 2 weeks, depending on the mass. After cooling, the casting goes to its first inspection. Ultrasonic testing searches for voids and inclusions inside, spots where the metal didn't fuse the way it should. X-rays check critical zones. If they find something significant, the casting goes back to remelt. No compromises. The rejection rate at this stage runs 3 to 8% depending on the casting's complexity, and that's completely normal for parts this size. Next, machining. Now, here in the shop floor, there are machines that made my jaw drop. The horizontal boring mill that machines the inner casing surface. It's about 60 feet long. The table where the part sits moves. The spindle stays put. The tool freely bores the bearing and seal mounting surfaces to an accuracy of plus or minus 0.5 of an inch. Why so precise? Because the rotor spinning inside at 1500 to 3600 revolutions per minute has a clearance between its blades and the casing of 50 to 150 microinches. 1% efficiency loss at a large power plant. That's millions of dollars in extra fuel costs per year. The rotor is the star of this story. It's a shaft carrying discs with blades, and it's the most complex part of the entire turbine. The shaft for a large steam turbine is a forging made from special chromium molybdenum vanadium steel, 20 to 40 feet long and weighing 20 to 60 tons in its rough state. A forging means you take a red-hot ingot of metal and just hammer it with a press weighing 5,000 to 50,000 tons to give it the shape you need. The grain structure of the metal during forging gets oriented along the shaft's axis. That's how you achieve torsional strength. After forging, the shaft goes through heat treatment again, then heads to the machine shop. Turning takes 2 to 4 weeks of continuous work on a lathe that's nearly 70 feet long. Chips fly, coolant flows, and machining away from that massive blank reveals the sleek shaft you saw in the drawings. This is the part where I'm always amazed. A gigantic component, yet precision like a watch mechanism. Blades are a separate production line. Steam turbines at large power plants have anywhere from 8 to 20 stages, and each stage is a disc with blades. First stage blades are small, sometimes less than 2 inches tall, because the steam there is still under high pressure and dense. Last stage blades are massive, up to 5 or 6 feet long on the largest turbines. These blades are forged and milled from iron-based alloys or stainless steel, and in their final profile, they have an aerodynamic shape with precision to within plus or minus 0.002 of an inch along the entire length. Each blade is checked for resonant frequency. It can't match the operating rotational frequency of the rotor, or else after a few thousand hours, a fatigue crack will develop from vibration. How they test this is simple. They tap the blade with a small hammer and listen with a special acoustic sensor. A very elegant method for such a serious problem. Assembling the rotor. This is when it starts to feel like an operating room. Bladed discs get mounted onto the shaft using shrink fitting. The disc gets heated to 300 to 400 degrees Fahrenheit. It expands, slides onto the shaft, then cools and grips the shaft with a force no bolt could ever match. No threads, no glue, just temperature difference and precision sizing. The interference fit when cold, 1 to 3/1000ths of an inch per inch of diameter. After assembly, the rotor gets balanced, and this takes 1 to 3 days. Balancing happens on a specialized rig, where the shaft spins on bearings while sensors register vibration. If there's any imbalance, metal gets removed from certain spots, or balancing inserts get installed. Allowable residual vibration on a large rotor, fractions of an ounce per inch of radius. If you think that's strict, you're thinking right. After assembly, the turbine heads to the test stand. At full operating parameters, pressure and temperature, they run the turbine for 24 to 72 hours. Sensors track bearing temperatures, vibration, steam leaks, power output. If anything goes outside the limits, stop, disassemble, analyze. There have been cases where they found a defect here that the X-ray missed initially. So the test stand isn't just a formality. It's the last line of defense before shipping. The finished turbine gets broken down into transport blocks, casing separate, rotor separate, auxiliary equipment separate. A large turbine rotor travels on a special trailer with hydraulic suspension, the kind you've seen on YouTube, with 18 axles moving at 20 miles per year. They coordinate the route a month in advance. Every bridge height and every turn width needs checking from the factory to the port or customer. Sometimes for one of these transports, they temporarily remove road signs and even take down power lines over the highway. I asked the chief engineer how many turbines they build per year. He said 12 to 20 of various types. That's it. Less than 2 per month. But each one runs for 30 to 50 years and generates electricity for hundreds of thousands of people every day. Some things don't need high volume production. In a world where every second counts, water produces over 50% of all clean energy on the planet. But have you ever wondered what price nature pays for this power? To build one hydroelectric plant, you need more concrete than for 10 skyscrapers. And the river has to be stopped. Its flow gets diverted into a tunnel. The riverbed gets dried out, and a foundation is poured that can withstand the pressure of thousands of tons of water. But behind every such structure lies not just engineering, but also mystery. By the end of this video, you'll discover how water becomes electricity that powers entire cities, and what dangerous price humanity pays for controlling a river. A hydroelectric power plant is where water transforms into electricity. The river's flow gets directed through turbines that spin and generate electrical power. It's a clean energy source with zero carbon emissions, and it works 24/7. But to make this possible, you need to build a dam, a massive structure that holds back the river, creates a reservoir, and controls water flow. The first and most crucial stage of hydroelectric plant construction is site selection. Engineers carefully study the terrain, geology, and hydrology of the region, looking for a narrow section of river with solid, stable banks. The ideal option is a natural gorge between mountains, where water already has significant elevation drop. This reduces the amount of earthwork needed and ensures powerful water pressure on the turbines. At the same time, it's important to have populated areas nearby that need a stable electricity source. The closer to the consumer, the lower the transmission losses. Such location also simplifies construction logistics, material delivery, equipment operation, worker housing. Site selection is a balance between natural conditions, technical capabilities, and human needs. This is where the foundation of future energy infrastructure gets laid. Before starting hydroelectric plant construction, you need to tame the river itself. Its flow gets temporarily redirected into a specially created bypass channel, or tunnel that's built alongside the future dam. This is a complex engineering operation that allows drying out the section where the main structure will be built. Working in the dry is critically important. Concrete work, rebar installation, and foundation work are impossible underwater. Such a river bypass can function for several months or even years while construction continues. After completing the main work, water gets returned to its new channel, now through turbines that start producing electricity. Once the river is diverted, builders move on to preparing the base, the foundation of the future dam. First, they carefully level the ground, remove unstable rock formations, compact the soil, and reinforce it with special materials. Then, concreting begins. They pour thousands of cubic meters of reinforced concrete, layer by layer, creating a monolithic structure. This foundation must be incredibly strong. It withstands not only the massive water pressure, but also possible earthquakes, seasonal water level fluctuations, and decades of operation. A mistake at this stage means disaster risk, so quality control here is maximum. They use laser levels, geodetic sensors, and every batch of concrete undergoes laboratory testing. From this very foundation grows the giant wall that changes the landscape and energy map of the region. The type of construction depends on local terrain and river characteristics. If the banks are solid and located close to each other, they choose an arch dam that transfers water pressure to the side rocks. If the river is wide and the terrain is flat, they build a gravity wall that holds back water with its own weight. In any case, it's a gigantic structure. Height can reach 984 feet, and length can span several hundred yards. For its construction, they use tens of thousands of tons of concrete, delivered by conveyors, mixers, and sometimes even cable cars. Work continues for years, often non-stop, day and night. Hundreds of people work on site: concrete workers, welders, surveyors, installers. Every stage requires precise coordination because a mistake can cost millions. The key stage of converting water into electricity happens in the lower part of the dam, where hydro turbines are installed. These are massive metal structures with blades resembling giant fans. When water from the reservoir gets directed downward under high pressure, it passes through the turbines, forcing them to rotate. This motion transfers to generators, devices that convert mechanical energy into electrical energy. A generator consists of a rotor and stator. When the rotor spins, electric current emerges in the magnetic field. All this happens with incredible precision. Even a small balance disruption can stop the system. To ensure stable operation, turbines get regularly serviced, cleaned of sediment, and temperature monitored. The result is powerful electricity that enters the grid and powers cities, factories, schools. Right here, in the depths of the concrete wall, the energy that drives the modern world is born. When all main structures are completed, foundation, dam wall, turbines, and generators, comes the moment of returning the river to its new channel. Engineers block the bypass canal, and water again gets directed toward the dam, but now in a controlled manner. It begins gradually filling the reservoir that formed behind the concrete wall. This process isn't quick. To avoid sudden level changes that could damage the structure or cause landslides, filling happens in stages. Sometimes this takes weeks or even months. Meanwhile, they monitor bank conditions, water levels, wall pressure, and turbine operation. When the reservoir reaches optimal level, the hydroelectric plant enters normal operation. It starts steadily producing electricity that enters the grid. To build one dam, they use enough material to construct 10 modern skyscrapers. This isn't an exaggeration. Concrete gets poured in layers, day and night, thousands of tons at a time. It's delivered by conveyors, mixers, barges, sometimes even cable cars. Such volume is needed to create a monolithic wall capable of restraining a river. But concrete is only part of the story. Water held back by the dam exerts colossal pressure. On every square foot of wall, dozens of tons of force. It's like several trucks pressing simultaneously on a door-sized area. Such pressure doesn't just affect the structure, but also creates potential for energy production. The greater the water drop height, the more energy can be obtained. Water flow gets directed through turbines that spin and drive generators. All this without burning fuel, without emissions, just nature's force. One large hydroelectric plant can provide electricity to millions of people. That's schools, hospitals, factories, neighborhoods, entire cities. In some countries, hydropower is the main electricity source, stable and ecological. When they build a dam, the river stops flowing freely. It gets restrained, redirected, accumulated. This changes the landscape. Valleys, forests, fields get flooded. Dozens of square miles of territory where people once lived, trees grew, and animals ran can end up underwater. Sometimes entire villages need relocation. Roads, bridges, and cemeteries need moving. It's a painful process requiring social support, compensation, and careful planning. At the same time, the river's life changes. Water flow becomes controlled, affecting fish accustomed to seasonal migrations. For example, salmon or sturgeon can lose access to spawning grounds if special fish passages aren't provided. Channels or ladders that fish can use to bypass the dam. Without them, populations decrease and sometimes disappear completely. Water's chemical composition also changes, along with its temperature and oxygen levels. In reservoirs, water stagnates, which can cause algae blooms or death of some species. The region's microclimate changes. It becomes more humid, fog appears, wind patterns shift. That's why modern projects try to minimize ecological damage. Engineers work together with ecologists, hydrobiologists, and geographers. They create fish passages, plant new forests, relocate rare species, and form artificial islands for birds. In some cases, they even create new ecosystems, wetlands and floodplains that compensate for losses. A hydroelectric plant is a powerful source of clean energy, but it shouldn't be a source of destruction. Balance between technical progress and nature is the main challenge of the 21st century. And this is where new construction ethics are born, not just to build, but to preserve. Every year, humanity mines nearly 2.5 billion tons of iron ore worldwide. That's over 5 trillion pounds of metal, without which we wouldn't have skyscrapers, roads, or even your smartphone. Iron drives civilization, but few people know where it truly comes from. Because every piece of this metal isn't just ore from a quarry, it's actually a fragment of an ancient star's explosion. And today, you're going to learn something most people don't even suspect. Stick around till the end. There's a hidden answer there that will completely change how you think about iron. The global iron production is an incredibly massive process that drives industrial development and shapes the modern world. Every year, the world extracts nearly 2.5 billion tons of iron ore, or more than 5 trillion pounds. This ore is the primary raw material for steel, without which we couldn't imagine building skyscrapers, cars, bridges, or even modern machinery. The leading iron ore producers are China, Australia, and Brazil. Australia, for example, mines more than 900 million tons per year, which is roughly 2 trillion pounds, making it the world's largest ore exporter. China, while producing significant amounts of its own ore, is also its biggest consumer, using nearly 1,200,000,000 tons annually for steel production. Iron ore mining involves massive quarries where giant trucks haul hundreds of tons of ore in a single trip. For example, one modern Australian mining truck can carry over 400 tons of ore at once. That's equivalent to the weight of more than 270 average cars. The global iron industry keeps pushing forward. Thanks to innovations in extraction technology and reduced energy consumption, production is becoming more efficient and environmentally friendly. Take the United States, for instance. They're implementing new systems to cut carbon emissions in steelmaking, gradually transforming traditional approaches to the industry. Iron demand is skyrocketing worldwide, especially in developing nations where they're building roads, railways, and massive infrastructure projects at breakneck speed. Simply put, iron is the real engine driving global development, and its production is a powerful indicator of economic strength. The iron we pull from the Earth's crust has cosmic origins. It was formed in the distant past, long before our planet even existed. Most of the iron in the universe was born in the hearts of ancient stars through processes called nuclear fusion. When a massive star reached the end of its life cycle, it exploded as a supernova, blasting heavy elements, including iron, out into space. This cosmic dust and gas gradually came together over time, forming molecular clouds that eventually compressed into protoplanetary disks. Earth's iron is what remains of these ancient stellar explosions, preserved and woven into the very fabric of our planet. That's why iron is one of the most abundant metals on Earth. During Earth's formation, over 4.5 billion years ago, the early planet was molten due to intense gravitational compression and frequent meteorite impacts. During this period, heavier elements, including iron, sank towards the center, forming the planet's core. Today, it makes up roughly 1/3 of Earth's total mass, and that's exactly why our planet has its unique magnetic field. The iron core powers this protective shield. Iron in the upper layers of the planet forms mainly as iron ore, a mixture containing oxides and other iron compounds. It's distributed throughout Earth's crust and mantle, and that's where we extract it from to create metal for every aspect of our lives. From iron's origins in stars to its crucial role in shaping our planet, this metal has traveled an incredible journey before becoming part of buildings, machines, and even your smartphone. So every piece of iron in the world is essentially a cosmic artifact, carrying within it the history of the universe and our planet's shared story. Iron almost never occurs in pure form in Earth's crust. It's hidden within numerous minerals, oxides, sulfides, silicates, carbonates, and other compounds. The most common iron minerals are hematite, magnetite, siderite, limonite, and pyrite. The iron content in these ores ranges from 10 to 70% or more, depending on the type and quality of the ore. To get metallic iron, you need a pretty aggressive and complex technological approach. In industry, the main method is the blast furnace process, where iron ore gets heated in a blast furnace at extremely high temperatures, around 2,900 degrees Fahrenheit. There, under the action of coal and other additives, the ore is reduced, meaning oxygen is separated from the iron, and molten metallic iron forms, which collects at the bottom of the furnace. Other methods, like direct reduction of iron, are used to extract metal from finer concentrates in the form of iron powder or sponge iron, which can then be remelted. So, iron gets freed from minerals through engineering processes that demand extreme temperatures and chemical reactions. This aggressive approach is what transforms the iron buried in ores into strong metal, the foundation of modern civilization. The molten metal pools at the bottom of the furnace, separating from the slag, impurities that float to the surface. Pig iron typically contains 3 to 5% carbon and other impurities, so it needs further processing. The next stage is the converter process. Here, molten pig iron from the blast furnace gets transported to an oxygen converter, where a jet of oxygen further oxidizes excess impurities and carbon. The result is steel with controlled carbon content, maximum 2%, depending on the steel grade. The molten steel then moves to the casting lines. This is where slabs are formed, massive flat ingots ranging from about 6 to 12 inches thick and up to several feet wide. A single slab can weigh dozens of tons. These slabs are an intermediate product that's then sent to rolling mills, where they're transformed into flat sheets, strips, or other profiles for future use in manufacturing structures, automobiles, construction rebar, and many other products. It's important to note that this entire technological chain requires high energy intensity and precise control of parameters, temperature, chemical composition, and processing time. Engineers control the process with high precision to achieve the necessary steel quality, strength, and durability. Besides traditional blast furnace production and converter refining, modern metallurgy increasingly uses electric arc furnaces, where steel scrap is remelted with molten iron, added to save resources and reduce environmental impact. The process starts with loading steel scrap into the furnace, pieces of metal, production waste, or old metal products. To improve steel quality and optimize melting, iron particles or iron concentrates are sometimes added to the scrap metal. After loading, the electrodes lower until they make contact with or get close to the scrap, and current flows through them. An electric arc forms between the electrodes and the charge, reaching temperatures up to 6,300 degrees Fahrenheit. Heating the charge under the arc's influence causes the scrap metal to melt rapidly. The molten steel forms a pool of liquid metal that mixes intensively thanks to electrodynamic vibrations and natural convection. This ensures uniform heating and metal composition. To purify the molten steel from unwanted impurities, oxygen is introduced into the furnace through special tuyeres. The oxygen oxidizes carbon, sulfur, phosphorus, and other harmful elements, forming slag that's easily removed. Alongside this, fluxes are added, materials that help neutralize impurities, improve slag formation, and protect the metal from air exposure. Refining continues until the desired chemical composition is achieved. When the metal reaches the required quality and temperature, it's poured from the electric arc furnace into special ladles, containers for transporting liquid steel to the next processing stages. On continuous casting lines, the molten metal is transformed into slabs. The weight of a single slab can reach anywhere from 20 to 30 tons. These billets serve as the foundation for further rolling into sheets, bars, pipes, and other metal products. The main advantage of electric arc furnaces is that they can run almost entirely on scrap metal, which dramatically cuts down the need for mining iron ore and slashes energy consumption. This makes steel production way more eco-friendly and cost-effective. The furnace is constantly monitored by operators who adjust the current strength, voltage, and oxygen flow to optimize melting and hit the exact steel specs needed. Graphite electrodes wear down over time from the extreme heat and need to be replaced regularly. Every year, humanity produces over 4 billion tons of concrete, more than any other material on the planet. It's what our cities, bridges, and roads are built from. But every crack is like a tiny timer ticking toward destruction, started the moment water seeps inside. Now imagine concrete that actually lives, breathes, and heals itself. No people, no repairs. Deep in labs across the Netherlands, USA, and Japan, a game-changing material is being born. Inside it, bacteria or microcapsules that can seal cracks on their own, just like skin healing after a wound. How is this even possible? How did a lifeless material gain the ability to regenerate? Stick around until the end, and you'll find out how scientists brought concrete to life. Self-healing concrete. Sounds like something out of a sci-fi movie, but it's already here. Scientists invented it to solve one of construction's biggest headaches: cracks. Regular concrete starts drying out and cracking over time from temperature swings, moisture, or just plain stress. And a crack isn't just a scratch. Water gets inside, the rebar starts rusting, the structure weakens, and eventually, you're looking at expensive repairs or even a collapse. That's why researchers decided to create concrete that can patch itself up, no human help required. Sounds crazy, but it's actually pretty logical. There are two main technologies that make this possible: microbiological and mineral. The first one uses real living organisms. So-called bioconcrete was developed by Dutch researchers, and the principle is pretty straightforward. They add special bacteria to regular concrete mix, usually Bacillus pseudofermis or Bacillus conii. These bacteria can stay dormant for years, like seeds in dry soil. Along with the bacteria, they add nutrients, usually calcium lactate. And while the concrete stays intact, the bacteria just sleep. But when a crack forms and moisture gets in, they wake up. That's when the real microscopic work begins. The bacteria start consuming the nutrient substrate and, through their life processes, produce calcium carbonate, basically the same mineral that makes up seashells and limestone. That's what seals the crack from the inside, like the concrete is fixing itself. The results are impressive. Micro cracks up to 0.03 of an inch can disappear completely within a few weeks. And all without human intervention, purely thanks to nature that's been built into an artificial material. The second technology is less alive, but no less impressive. Instead of bacteria, it uses chemistry. Tiny capsules are added to the concrete containing an active substance inside. For example, epoxy resin or sodium silicate. These grain-sized capsules are evenly distributed throughout the mix. When the concrete cracks, some of the capsules burst too. The substance inside comes out, fills the crack, and hardens on contact with air or moisture. The result is the material literally heals itself. It's similar to how certain car paints can heal scratches with heat, except this process is way more complex and large-scale. The advantage of this approach is that it works even in dry conditions, where bacteria might not activate. The downside is cost. Creating the capsules is more complex, so this concrete is pricier. But when you calculate the cost of repairing bridges or tunnels, it becomes clear. The payoff is huge. Interestingly, these technologies don't cancel each other out. Some companies are experimenting with combining biological and chemical methods to create concrete that could self-heal under any conditions. Underwater, in the desert, or in freezing cold. Testing shows that structures made with this concrete last 2 to 3 times longer than regular ones. Bridges, roads, dams, parking garages, all of this can be made nearly eternal. For example, the Netherlands already built a lakeside lifeguard station using bioconcrete, and after several years, it hasn't needed any repairs. The idea is spreading fast around the world. In the US, these materials are being tested in bridges, in the UK, in sidewalk paving, and in Japan, even in concrete for coastal reinforcements that have to withstand salt water. Regular concrete, even the highest quality, has a shelf life, roughly 50 years. After that, cracks start appearing, water penetrates inside, rebar rusts, and the structure gradually weakens. Self-healing concrete changes these rules. Thanks to bacteria or microcapsules, it can heal microdamage before it becomes a problem. That's why the service life of structures can nearly double, from 100 to 120 years. That means one bridge or building can stand for 2 human generations without major repairs. Sure, this material isn't cheap yet. It costs several times more than regular concrete, on average 3 to 5 times more. But if you look at the long game, it's totally worth it. Maintaining, repairing, and restoring structures costs governments and companies millions of dollars every year. Self-healing concrete cuts those costs to a minimum. Basically, it's like buying a car that changes its own oil and fixes its own brakes. Expensive upfront, but then smooth sailing and economical. The Netherlands became the real home of self-healing concrete. Right here, at Delft University of Technology, The idea emerged to add living bacteria to the mix that could repair concrete from the inside. The man behind this idea is Dutch microbiologist and engineer Hendrik Jonkers. Nature inspired him. He noticed that certain bacteria can survive in limestone rock and create mineral deposits, filling micro cracks in stone. That's when Jonkers asked himself, if nature can heal stone, why not make concrete that does the same? In the early 2000s, he started experiments with different bacterial strains, looking for ones that could withstand concrete's alkaline environment and stay viable for years. After numerous trials, the best candidates turned out to be Bacillus pseudofirmis and Bacillus conii, spores that can sleep for decades and activate only when moisture appears. Jonkers added them to concrete along with a food source, calcium lactate. The results were mind-blowing. When the concrete cracked, the bacteria woke up and produced calcium carbonate, which sealed the cracks like natural glue. Jonkers called his invention bioconcrete, and soon the whole world was talking about it. Later, Delft University launched a project to test bioconcrete under real-world conditions. In 2015, the Netherlands built the first lakeside structure using this material. Years later, it remained in excellent condition without any repairs. Now Jonkers' lab is working with construction companies and governments from other countries, perfecting the formula to make it cheaper and more accessible. The USA and UK bet on the mineral technology for self-healing concrete, which doesn't require living organisms, but works through special microcapsules with healing substances inside. These countries are actively investing in research on materials that can automatically restore minor damage without human involvement. The principle is pretty simple, but looks impressive. Capsules or microcapsules filled with special gel, epoxy resin, or sodium silicate are added to the concrete mix. When the concrete surface stays intact, the capsules preserve their contents without reacting with the environment. But as soon as a crack appears, the capsule ruptures and the liquid flows into the damaged zone. On contact with moisture or oxygen, the substance hardens, gluing the crack edges together and returning the structure's original strength. These systems are currently being tested in US Army labs and British research centres, including Cambridge University. In the UK, they're even building experimental road and bridge sections with this material to track how it behaves under rain, vibrations, and temperature swings. American experts went even further. They're experimenting with capsules that can activate multiple times. Inside these capsules are microgels that not only fill cracks, but also expand on contact with water, creating a hermetic barrier against corrosion. This is especially crucial for bridges and skyscrapers in coastal cities, where concrete constantly faces moisture and salts. Test results show that cracks up to a few hundredths of an inch wide can seal themselves in less than a week. And if the damage is larger, the process takes longer, but still happens without human involvement. Such technologies can significantly extend the service life of roads, tunnels, and even military structures, which is especially valuable under extreme loads. In every country, asphalt is just a road. But in Dubai, it's a challenge to nature. Here, air temperatures reach 122 degrees in the shade, while the road surface heats up to 160. Regular asphalt would melt within just a few days, but engineers found a way to make it survive. Polymers that hold their shape even at 176 degrees, geotextile membranes that breathe, and sensors that detect defects before human eyes can spot them. Why don't these roads melt like ice in the sun? And what strange technology did they test to make them actually dry after rain? Watch till the end. The finale will surprise you. Standard asphalt consists of stone aggregate and bitumen, a dark, thick substance that holds the mixture together, making it uniform and strong. However, bitumen has one weakness. It starts to soften at temperatures around 113 degrees Fahrenheit. For countries with moderate climates, this isn't a problem since road surfaces rarely reach such heating levels. But Dubai has completely different conditions. There, summer air can heat up to 122 degrees in the shade, while the road surface under direct sunlight can reach 160 degrees. Under such conditions, regular asphalt would literally behave like warm rubber. It would become soft, start deforming under vehicle weight, and in places simply slide off slopes. Plus, sharp temperature changes between scorching days and relatively cool nights would cause cracks to appear. In countries where occasional short heat waves occur, people might not immediately notice these processes. Sure, we sometimes get 104 degrees in summer, but such temperatures don't last long, and the surface deteriorates slowly, gradually. In Dubai, however, high temperature isn't just present, it's constant and stable for several months. This means asphalt is under continuous stress, and if you don't account for this factor, the road literally won't survive. That's exactly why engineers had to find a solution that would allow asphalt to maintain its shape even under extreme heating conditions. They replaced regular bitumen with modified bitumen, with polymer additives that change its physical properties. Such bitumen holds its shape at temperatures up to 176 degrees Fahrenheit. This means even when the road surface heats up to maximum levels, the material still remains stable, doesn't flow, and doesn't change structure. The difference might seem small at first glance. What's a few dozen extra degrees? But this exact difference makes Dubai's roads smooth, even, and durable, even when it's almost impossible to breathe from the heat around you. So what is this modified bitumen? The process is based on mixing bitumen with polymer additives. Polymers act like a reinforcing network at the molecular level. They stretch the bitumen structure, making it more elastic and heat-resistant. As a result, the asphalt doesn't soften. It maintains stability and shape even when heavy bus or truck wheels press on it for hours. The mixing process also isn't limited to just adding polymers. It's crucial to properly select the stone aggregate composition. Stones of different sizes create a framework-like structure, and bitumen here acts not as the main material, but rather as what connects the elements together. If the aggregate is selected incorrectly, bitumen will have to take on too much load, and even the modified mixture will lose stability. Therefore, asphalt composition is always a precise calculation of material ratios that don't just connect, but work as a unified system. But asphalt is just the surface. Hidden beneath it is a multi-layered sandwich that determines the road's durability. The first layer is sand, but regular sand won't work. It's mobile, can shift, and the road would lose its evenness within months. So sand is stabilized by mixing it with cement or special substances that make the mixture less mobile. Next comes a crushed stone layer that provides hardness and distributes load. Special geotextile fabrics can be laid between layers, preventing settling and material mixing. Geotextile works as a membrane that allows water to pass through, but doesn't let soil particles mix. This keeps the construction stable for many years. The way asphalt is actually laid also plays an important role. Work is usually done at night when temperatures are lower. This is necessary so bitumen cools evenly and gains the required hardness. If you lay asphalt during daytime heat, its surface will cool unevenly, creating stress in the structure that will eventually lead to microcracks. After laying, roads are regularly checked using special machines equipped with sensors and thermal imaging cameras. If sections are found where temperature is too high or irregularities appear, they're repaired immediately, not waiting until the problem becomes visible to drivers. Experiments with cooling coatings deserve special mention. In some districts, asphalt is painted or covered with a special compound that reflects sunlight and reduces surface heating by 10 to 15 degrees. This is important in pedestrian areas since road surface temperature affects how hot the air gets at foot level. This way, even a regular walk becomes less exhausting. In Dubai, roads aren't left unattended until large potholes appear. Control happens constantly and systematically. Special vehicles with measuring equipment travel highways and city streets, recording the smallest irregularities. Sensors read surface deviations, and computers compare them to standards. If there's suspicion of overheating or beginning deformation, the section is checked with thermal imaging cameras. High temperature indicates that bitumen is losing rigidity, and the surface might start settling. Thanks to such monitoring, repairs are done not when it's too late, but when the first changes begin. Repair work is conducted mainly at night when temperatures are lower and material cools evenly. This extends the road's service life and avoids repeated damage. The approach is based on the idea that infrastructure should work continuously, not wait for the moment when it becomes a problem for drivers. According to Dubai municipality data, after switching to polymer-modified mixtures, the number of deformation waves on roads decreased by approximately 40% during the first 2 years. Meanwhile, road surface service life increased on average from 7 to 10 years to 12 to 15 years before the first major repair. This significantly reduces overall infrastructure costs. Although initial polymer asphalt installation costs are higher by approximately 15 to 20%, long-term savings can reach 50% due to reduced repair needs. There's also data on experimental light reflective coatings being tested in residential areas and near pedestrian zones. On average, such coatings reduce road surface temperature by 10, or even all 14 degrees, depending on conditions. According to observations, in areas with cooling roads, air temperature at pedestrian foot level also drops by 2 to 3 degrees, reducing thermal load on people and making outdoor stays more comfortable. Statistics also show that, with early detection of surface microdefects, their elimination takes on average 3 to 6 hours, while if you wait for visible damage to appear, repairs can last from several days to several weeks and require closing road sections. Therefore, the city focuses on regular monitoring. In 1 month, control vehicles can cover over 80% of the city's road network. Dubai once tested asphalt that absorbs solar energy, then radiates stored heat at night to dry roads faster after rare rainfall. Turns out, the surface works like a giant thermos. During the day, it accumulates energy, and at night gradually releases it. The experiment showed such roads can dry 30% faster. And this is really needed, because after desert rain, water doesn't absorb into the ground, but can stand on asphalt for hours or even days. So the technology solves a problem that doesn't even exist in most countries. You know how this experiment ended? They extract it in mountains where stone is born from flames and pressure capable of crushing anything alive. Its formation takes hundreds of millions of years, and today, people cut it with diamonds at a speed of 20 miles per hour. But what if I told you that this shiny material, used to decorate palaces and statues, was once the bottom of an ancient ocean? And that every slab of marble is a frozen story of life, death, and time? Watch until the end, and you will see how nature creates its own masterpiece, and people try to uncover its secret. Marble is not just a beautiful stone for decoration or sculpture. It is a material that has millions of years of geological transformation behind it. Its journey begins deep underground, where temperature and pressure change ordinary rocks beyond recognition. The basis of most marble is limestone, a sedimentary rock formed mainly from calcite. Limestone is formed at the bottom of ancient seas and oceans from the remains of marine organisms, corals, mollusks, foraminifera. Over millions of years, these fragments settle, compact, and cement together under pressure to form thick layers. When such layers fall into a zone of tectonic processes, where the Earth's crust moves, compresses, or subsides, they sink into deeper layers of the Earth. There, the temperature can exceed 1,200 degrees Fahrenheit, and the pressure reaches 1,000 atmospheres. Under these conditions, metamorphism begins, the process of transforming rocks without complete melting, but with a change in their structure. During metamorphism, the calcite crystals in the limestone begin to recrystallize. The old grains disappear, and instead, new ones grow, larger, tightly fused together. This process gradually transforms the loose sedimentary rock into a solid monolith with a characteristic shine and granular texture. It is this structure that gives marble its famous ability to be polished. The variety of colors and patterns in marble is the result of impurities that got into the limestone during its formation or metamorphism. If there is iron in the rock, the marble acquires reddish or yellow hues. Graphite or organic matter makes it gray or black. Impurities of serpentinite or chlorite add green tones. Quartz, dolomite, and pyrite create veins, the same patterns that make marble seem alive. Marble is not formed instantly. The process can take hundreds of millions of years. In places where tectonic plates collide, for example, in the Himalayas, the Alps, or the Apennine Peninsula, the rocks experience the most intense pressure. That is why such areas have become world centers for marble quarrying. For example, Carrara in Italy, where white marble of extraordinary purity was formed. During metamorphism, degassing also occurs, the release of carbon dioxide that remained in the pores of the limestone. Because of this, the structure of marble becomes almost non-porous. This density makes it durable, but also more brittle with sudden changes in temperature. In some cases, the process of marble formation can be partially reversible. If the temperature is too high, the calcite begins to melt, forming intermediate forms between metamorphic and igneous rocks. Such transitional marbles are found in areas of contact between limestone and magmatic intrusions, for example, near granite massifs. Another interesting feature is the zonation of formation. In nature, it is rare for an entire layer of marble to have the same structure. In different areas, the pressure and temperature are different, so some layers are coarse-grained, others are fine-grained, some have veins, others have a uniform color. This explains why even within a single quarry, marble of a completely different appearance can be extracted. When geologists study deposits, they are looking for precisely those places where the limestone has undergone complete metamorphism, but has not been destroyed by excess heat or deformation. Sometimes these layers lie at a depth of several hundred feet. Sometimes they come right to the surface, as in Tuscany or Greece. The quarrying and processing of marble is no less fascinating a process than its formation. The modern marble industry combines powerful machinery, precise laser technologies, and artisanal craftsmanship that has barely changed since the time of Michelangelo. The first stage is the identification of the deposit. Geologists conduct research on mountain ranges, using georadar, laser scanning, and drilling samples. The goal is to find a layer of marble of the required thickness, color, and uniformity. Sometimes the required layer lies almost on the surface, as in Carrara in Italy, or on the island of Paros in Greece. In other cases, it has to be uncovered, removing tens of feet of rock from above. When the site is prepared, the separation of marble blocks begins. Once, this was done with explosives, but now much more precise and safer methods are used. The main tool is diamond wire saws. This is a steel cable on which hundreds of diamond segments are strung. The cable is stretched between two pulleys and rotates at a speed of over 20 miles per hour, gradually cutting the stone like a string cuts cheese. Thanks to a water cooling system, the cut is even and smooth, without cracks. Another method is drilling vertical and horizontal holes in the rock, through which a diamond wire is then threaded. This forms the rectangular contour of the block. When the cuts are connected, a huge piece of marble, usually weighing from 20 to 50 tons, is separated from the mountain massif. It is propped up with hydraulic jacks, steel wedges are inserted, and the block is gradually released, preventing a sudden fall. Next, the blocks are transported from the quarry to processing plants. On the slopes of mountains, powerful tracked loaders and platforms on heavy trailers are often used for this. In mountainous areas where there are no roads, marble is sometimes lowered by special cable systems, a kind of funicular that leads from the quarry to the valley. In the workshops, the blocks are cut into slabs or blanks. For this, gang saws are used, large frame machines with dozens of steel blades, between which an abrasive mixture with water is fed. In modern production, they have been replaced by diamond circular saws, or laser cutting machines. The cutting accuracy reaches fractions of a millimeter. After cutting, the surface of the slabs is ground with abrasive stones of different grits, gradually moving from rough grinding to mirror polishing. If the marble is intended for architectural projects, it is further strengthened. A thin layer of resin or fiberglass is applied to the backside. This prevents chipping during transportation and installation. For sculptures, such reinforcement is not done. On the contrary, they look for a stone with a uniform texture without microcracks. Polishing is a separate art. It is performed on large machines where a series of round abrasive discs pass over the surface, gradually giving it a deep shine. To achieve a perfect effect, powders of tin or cerium oxide are used. It is they who reveal the structure of calcite, and the marble begins to play with reflected light. After polishing, the marble slabs are marked and sorted by color, pattern, and quality. Part of it is sent for export, another part to workshops for carving, facing, or manufacturing architectural details. Sculptors work with marble much more delicately. They use hand chisels, hammers, and now, pneumatic tools that allow them to carefully remove the stone layer by layer. Even with modern technologies, the art of marble processing remains semi-artisanal. It requires an eye, a touch, and an understanding of how the rock behaves. At the end, the marble products are coated with protective waxes or silicone impregnations, which enhance the shine and protect the surface from moisture. For interior work, softer compositions are used. For facades, water-repellent, UV-resistant ones. Quarries are usually located in mountainous areas that are difficult to reach. To cut blocks weighing from 20 to 50 tons, expensive equipment is needed. Diamond wires, cranes, hydraulic jacks. At the same time, about 30 or 40% of the quarried stone is suitable for commercial use. The rest is cracked or defective blocks that go to waste or are crushed into crumb. Due to the mass and fragility of the slabs, they are transported on special trailers or containers with cushioning. For imported marble, delivery can account for up to 30% of the final price. Every year, over 1,000 giant ships are sent worldwide for scrapping, each weighing up to 50,000 tons and stretching nearly 3 football fields in length. It's like dismantling an entire floating city, with hundreds of miles of cables, tons of toxic substances, and metal worth millions of dollars. One mistake, and an environmental disaster is inevitable. But here's the most amazing part. Inside each of these massive vessels hides something that turns scrapping into a real treasure hunt. Workers risk their lives among plasma cutters and toxic fumes to extract these valuables. What exactly are they looking for? And why have some countries turned ship graveyards into a multi-billion-dollar business whose dark side everyone keeps quiet about? Stay tuned. What you'll learn next will make you look at every ship in port with completely different eyes. Why is ship recycling so important? Vessels that we typically imagine as enormous floating megastructures can be nearly 1,000 feet long. Their weight sometimes reaches tens of thousands of tons, making them among the largest man-made objects created for sea travel and cargo transportation. But beyond their massive dimensions, these ships have extremely complex internal structures. Hundreds of feet of cables, pipelines, shafts, and various safety and comfort systems, plus countless different elements and mechanisms that perform different functions. This entire architecture isn't just scrap metal, but a complex organism that must be very carefully and properly dismantled when the ship reaches the end of its service life. It's critically important to properly remove all hazardous substances from the vessel that may have accumulated during its operation. These can be bioactive substances, toxic paints, fuel residues, lubricants, chemicals that, if handled improperly, can contaminate the sea, soil, and air, causing serious environmental problems. Without proper preparation, dismantling such a vessel can turn into a natural disaster. However, scrapping these maritime giants also has a very bright positive side. The metal from which the ship is made is excellent and valuable raw material that can be recycled and returned to production. This metal is used for building houses, machines, construction structures, and also for creating new vessels. This way, it's possible to reduce the need for smelting new steel, save energy and resources, and also reduce the amount of waste. Metal recycling from ships becomes an important link in the closed loop of modern industrial economy. Scrapping such huge objects also makes it possible to free up ports where old ships are standing, so new, modern vessels can take their place. This allows optimizing the work of naval bases and promotes fleet renewal. Additionally, proper recycling helps reduce operational costs for maintaining old ships and improves environmental standards in the maritime industry overall. The ship is delivered to special ship graveyards. These are usually coastlines with shallow water or special slipways. These locations aren't chosen randomly. Shallow water coastlines allow easy approach of the ship to shore, where it can be safely moored and dismantling can begin. Often these are small bays or beaches where the giant vessel is specially brought, so it doesn't interfere with maritime traffic and doesn't damage port infrastructure. Slipways, in turn, are large platforms or special structures where the ship is placed for dismantling on land. They're equipped with everything necessary for convenient and safe work: crane equipment, metal cutting tools, waste removal systems. One of the main tasks for specialists is ensuring environmental safety. After all, during operation, the ship accumulated many substances that, if handled carelessly, can harm the environment. These can be not only lubricants and fuel residues, but also toxic paints or chemicals. Therefore, the entire dismantling process begins with removing all such substances. Fuels and lubricants are drained into special containers and taken away for recycling or disposal to avoid getting into water or soil. Similarly with electronics and furniture, everything that could potentially harm nature is removed as a priority. This stage requires speed and maximum caution so that environmental standards aren't violated. After the ship is cleared of all hazardous and household items, the direct dismantling of the hull begins. And this is the most complex and dangerous part. Using special plasma cutters and gas torches, large steel structures begin to be cut into small pieces. This involves both hand equipment and heavy machinery, cranes, lifts, special manipulators. Plasma cutting allows very precise, fast and efficient metal division that will later go for remelting. The dismantling process itself happens sequentially, stage by stage, starting with the most hard-to-reach or dangerous zones. Metal sheets, beams, decks, and internal partitions are carefully separated so as not to damage structures that might still be needed for analysis or recycling. The complexity is that giant elements are often unevenly distributed and may be under tension, and due to corrosion or hull deformation, some parts can unexpectedly drop or fall at any moment. It's also important to emphasize worker safety. During plasma cutting, hot sparks and toxic fumes arise, requiring special protection from workers, respirators, special clothing, and constant air monitoring. A small mistake or neglect of rules can lead to serious injuries and accidents. Therefore, at every step, the process is regulated by strict safety rules, and the entire site is covered by fire suppression systems and medical support. Dismantling the hull and main steel structures of the ship is, without doubt, an extremely important and complex stage of scrapping a giant vessel. However, after this large body of work is completed, the job doesn't end. Ahead lies another massive phase that requires no less attention and certain skill, as it concerns dismantling and sorting countless smaller, but no less valuable and complex materials. One of the most massive and complex processes is working with cables. The ship contains hundreds of miles of cable networks that provide power and communication between all systems. These are powerful steel cables with insulation made of plastic, rubber, and possibly using non-ferrous metals. Cables don't just remain at the recycling site, they're carefully removed, processed, and sorted. Separating the metal core from insulation materials makes it possible to send pure copper or aluminum for remelting, and the insulation layer for recycling as raw material for new polymers. Workers must act very carefully not to damage long cable pieces, and also observe safety techniques due to the presence of residual substances or rust. Another important category of materials is insulation materials that line or fill the ship's walls, technical rooms, and pipelines. Insulation is often made from special materials: mineral wool, polyurethane foam, or basalt wool. These substances help control temperature inside systems and ensure safety when working with hot or cold components. After removing insulation, it's sorted and sent to specialized enterprises where these materials can be recycled or disposed of without harming nature. Working with ventilation systems also requires thoroughness. Ventilation pipes and units that were used for air conditioning and circulation in different parts of the ship are dismantled and cleaned of dust, lubricant residues, or other substances. Metal elements of systems typically undergo quality remelting, and plastics or rubber often become raw materials for new products. Special attention is paid to water supply systems and sanitary installations. On board the ship are complex shut-off mechanisms, pipelines, fittings, mixers, tanks, and other equipment. Pipe parts and equipment are carefully separated, cleaned of sediment, lubricants, and other contaminants to be sent for remelting or appropriate recycling. After all, these materials may contain toxic substances, so their disposal or recycling happens strictly according to regulations. No less important is dismantling equipment from the engine room. There are engines, generators, pump systems, turbines, and other complex machinery that typically has significant weight and contains large amounts of metals, including non-ferrous ones. Such equipment is mainly repaired and reused or dismantled into parts, some of which undergo recycling. In individual cases, engines even go for sale as used spare parts, avoiding becoming scrap metal. Furniture, household appliances, lighting, and other interior items of the ship also aren't just thrown away. They're removed and sorted. Wooden, metal, or plastic parts undergo separate recycling or disposal. In some cases, furniture, if it's in good condition, is sold for reuse, and all paints, varnishes, and certain polymer materials are taken for environmental recycling to reduce pollution. Every 3 seconds worldwide, a new engine block rolls off the production line, the heart of a car that will withstand millions of explosions, temperatures over 4,600 degrees, and operate for decades without stopping. But how do you transform molten metal into a perfect mechanism with precision down to a micron? One mistaken dimension, and the engine will tear itself apart within minutes of operation. Every year, over 100 million of these blocks are manufactured, and each one goes through a hellish birthing process. Molten metal at 5,400 degrees, sand molds that self-destruct, and robots that cut channels thinner than a human hair. But there's one secret the manufacturers don't talk about. A mystery hidden inside every block that determines whether your car will go 60,000 miles or 600,000. Stay until the end. What you'll learn will forever change how you see what's happening under your car's hood. Let's start by understanding what an engine block actually is. It's the foundation that holds the entire engine together. Inside it are the cylinders where fuel combustion occurs, pistons that move up and down, and other critical components. The engine block must be strong, lightweight, and resistant to high temperatures. That's why manufacturing it is a complex process that demands precision and advanced technology. Everything begins with an idea. Engineers develop a concept for an engine that must be powerful, economical, and environmentally friendly. They use specialized 3D modeling software to create a digital model of the block. This allows them to account for every detail and test how the engine will perform under various conditions. Engine blocks are made from different materials, but the most common are cast iron and aluminum. Cast iron is strong and resistant to high temperatures, but heavy. Aluminum is lighter and dissipates heat better, but less durable. Sometimes composite materials or alloys are used to combine the advantages of both metals. After the engineering team completes all calculations, computer modeling, and finally approves the design of the new engine block, the true heart of the future automobile, the most interesting part begins: its birth in metal. The first and perhaps oldest step in metallurgy is casting. A massive shop filled with the hum of machinery, the smell of molten metal, and the glow of high temperatures. This is the foundry, where engineers' dreams become real components. First, a mold for the block is created. There are two main approaches to creating these molds, each with its own advantages. The first, and most common for large-scale production, uses sand molds. This is an amazing, though traditional method. First, they make a pattern of the future engine block, usually manufactured from wood or metal, and it's an exact copy of the block, but accounting for certain features, such as compensation for metal shrinkage during cooling. Then this pattern is placed in a special container, where it's tightly packed with a mixture of quartz, sand, clay, and organic binding agents. This mixture is compacted, then baked or chemically hardened, creating a strong but porous mold. After this, the pattern is carefully removed, leaving a cavity that precisely matches the shape of the future block. The most challenging aspect of sand molds is creating internal cavities, coolant channels, oil passages, cylinder bores. For this, they use so-called cores, separate elements, also made from sand, that are inserted into the mold. After pouring the metal and cooling, the sand is easily removed, leaving the necessary internal channels. The advantage of sand molds is their relative affordability per unit at large volumes and the ability to create very complex internal geometries. The second method, often used for aluminum blocks or smaller production runs, uses metal molds or permanent molds. These are stronger, reusable molds made from steel or cast iron. They're more durable and allow for parts with smoother surfaces and higher dimensional accuracy right from the casting stage. However, metal molds are much more expensive to manufacture, and it's harder to adapt them for creating the very complex internal channels found in engine blocks. Therefore, they're often combined with sand cores for internal cavities. The chosen material, cast iron or aluminum, is melted in a furnace at high temperature. For cast iron, this is typically over 4,600 degrees Fahrenheit. For aluminum, around 3,000 degrees. In massive induction or arc furnaces, metal scrap and pure ingots slowly transform into a glowing, liquid mass that shines bright orange or silvery light. This process includes precise control of chemical composition. Metallurgists add special alloying elements, such as silicon, magnesium, copper, in strict accordance with the recipe, to give the future block necessary properties: strength, wear resistance, lightness. The molten metal is constantly stirred and goes through refining processes to remove unwanted impurities that could reduce the quality of the finished part. Finally, the climax arrives: pouring. The molten metal, radiating intense heat, is carefully transferred from the furnace into special ladles, then into the prepared molds. This is the moment of maximum concentration and precision. The metal must fill every cavity of the mold, displacing air and completely matching its configuration. The pouring process can be gravitational, meaning the metal simply flows under gravity or under pressure, which ensures better mold filling and reduces porosity. After pouring, the mold remains for some time, so the metal can cool and solidify. This can take from several minutes to several hours, depending on the block size and metal type. When the metal has cooled and fully crystallized, the next stage occurs. The mold is broken apart. If it's a sand mold, it's simply destroyed using vibration or hydraulic hammers, freeing the newly created metal object. The sand is later collected and partially recycled. If it's a metal mold, it's opened, and the finished block is carefully extracted. As a result of this process, we get what's called a rough engine block. It's not perfect yet. Its surface is rough, it may have sand residue or so-called flash, small metal overflows at the mold seams. It doesn't yet have mounting holes, and it lacks the micron tolerances required for engine operation. But it's already a real block. Massive and heavy if it's cast iron, or surprisingly light if aluminum, but already with a clearly defined shape, ready for the next processing stages that will transform it into a high-precision part capable of withstanding incredible loads inside the engine. Mechanical processing is performed on specialized computer numerically controlled machines. The large, solid block is secured on a special table. Around it, various tools move, performing their work. Like a scene from some movie, isn't it? Let's start with the most obvious, cylinder bores. These holes must be perfectly round, have precise diameter, and be positioned exactly on one axis, since pistons will move within them. First, machines use large end mills to roughly remove material, creating preliminary holes. It's like carving out a large chunk from cheese. Then more precise tools come into play. Special boring cutters are used, which carefully remove the thinnest layers of metal, bringing cylinder diameters to the required size. This happens in stages, with constant dimension control. After this, cylinder walls undergo honing. This is final abrasive processing that creates very fine, cross-hatched scratches on the internal surface. These scratches retain lubricant, ensuring perfect lubrication of piston rings and minimizing friction, which is critically important for engine efficiency and longevity. Actually, the cylinder surface after this processing feels perfectly smooth to the touch, but under a microscope has the perfect structure for retaining an oil film. Next, oil and cooling channels. These systems that penetrate the entire block are vitally important. Oil channels deliver lubricant to all moving engine parts, such as the crankshaft, camshaft, pistons, ensuring their lubrication and heat removal. Cooling channels circulate coolant, removing excess heat generated during fuel combustion and maintaining optimal engine operating temperature. The internal, complex labyrinths of coolant and oil channels, as we mentioned, are formed during the casting stage using sand cores. But after this, they need to be opened and brought to perfect condition. For this, high-precision drills and mills are used to create inlet and outlet openings for these channels, and also connect them with other engine parts. Each hole must be positioned with millimeter, or even micron precision, so fluids can circulate freely. Today, we're not at some sleek, modern factory. We're heading back in time, to an era when the entire world was engulfed in flames, and one nation that had peacefully built cars and refrigerators did something absolutely mind-blowing. This is the story of the arsenal of democracy, how American industry churned out so much weaponry in just a few years, it could have armed several planets. And we're looking at its crown jewel, the legendary flying fortress, the B-17 bomber. I spent weeks digging through archival blueprints, photographs, and records to tell you how a country that was making sedans for housewives yesterday started rolling out one bomber every single hour. So it's December 1941. Pearl Harbor's in flames, and America enters World War II. And the first question facing the government: where do we get planes? The B-17 bomber, developed by Boeing. It's an engineering marvel, but they're building barely any, almost one at a time. And the country doesn't need dozens, it needs tens of thousands of these machines. So President Roosevelt throws down the gauntlet to American industry, and that industry answers. And how it answers. Enter automotive giants like Ford and aircraft companies Douglas and Lockheed. They're told, guys, forget about cars. From now on, you build bombers. And that's when the real madness begins. Picture this. Ford, a company that had never built planes before, constructs from scratch in the middle of a Michigan cornfield, the world's largest factory at the time, Willow Run. This isn't just a factory, it's an entire city under one roof, a mile long. Over 40,000 people work here, many of them women coming into manufacturing for the first time. And they face a task that seems impossible. Put the production of a giant, complex bomber on an automotive assembly line. Nobody had ever done this before. You get why it was women, right? When America entered the war, millions of men, factory workers, farmers, mechanics, put on military uniforms and shipped out to the front. And suddenly, the factories that needed to produce tanks, ships, and planes sat empty. The country faced a massive labor shortage. So the government and industry turned to people they'd barely considered for heavy manufacturing before: women. A powerful propaganda campaign rolled out. Famous posters showing a strong woman in a work bandana, flexing her bicep with the words, "We can do it," appeared across the country. And women answered the call. Millions of housewives, waitresses, secretaries, and recent high school graduates went to work in the factories. For them, this wasn't just a paycheck. It was patriotic duty, a way to do their part for victory, while their husbands, brothers, and sons fought thousands of miles from home. They proved they could do men's work just as well, sometimes better, becoming the unstoppable force that allowed American industry to work miracles. And here's where the American government and industry made some incredibly powerful moves. First, the government essentially forced Alcoa to share its technology and funded the construction of dozens of new, massive aluminum plants across the country. Entire cities were built, for example, in the industrial states of Washington and Tennessee. Why there? Because aluminum production is an insanely energy-intensive process. It relies on electrolysis from alumina, and that requires cheap electricity. And in these exact regions, the government had just finished building giant hydroelectric dams on the Columbia and Tennessee rivers. It was a perfect match. Huge amounts of clean, cheap energy waiting for someone to use it. Second, raw materials. The main raw material for aluminum is bauxite. Most of it had been imported from South America before the war. When the war started, German submarines began hunting merchant ships, and that route became dangerous. So America dramatically ramped up mining of its own bauxite, mainly in Arkansas, and secured the sea routes from the Caribbean as much as possible. But the most amazing part of this story is the grassroots movement. The government launched a massive patriotic campaign with the rallying cry, "Turn in aluminum for victory." School children, housewives, Boy Scouts, the entire nation started collecting aluminum scrap. People turned in old pots, pans, milk cans, parts from household appliances. It didn't have decisive economic significance, but it had a colossal psychological effect. Every American felt that their old pot could become part of a flying fortress wing that would fly off to strike the enemy. As a result of these titanic efforts, in just a few years, from 1940 to 1943, aluminum production in the US increased sixfold. The country didn't just cover its own needs, it started supplying this strategic metal to its allies. And that's how, through the combination of government will, industrial might, and the patriotism of ordinary people, America transformed a scarce pot metal into an endless stream of winged metal that became the lifeblood of its bomber armada. After stamping, each part needed 2 holes drilled on each side for rivets. And that's when the women stepped onto the stage. The legendary Rosie the Riveters. Thousands of young women who just yesterday were housewives or waitresses now stood at workstations, drilling these holes with incredible speed and precision. And then the real concert began. Thousands of pneumatic riveting hammers pounding aluminum simultaneously, creating a deafening non-stop roar. This was the sound of the arsenal of democracy being forged. Women worked in pairs. One held a massive bucking bar from the inside, while the other hammered the rivet from outside. Each rivet had to be perfect, because the aircraft's strength depended on it. And this is where Ford unveiled its main automotive trick: modular assembly. They didn't try to build the entire airplane in one place. Instead, they broke it down into large sections, or modules. In one shop, thousands of people assembled just the nose section of the fuselage. In another, just the center section with the bomb bay. In a third, gigantic wings, each over 50 feet long. Each section was assembled on its own mini assembly line, where it was packed with everything necessary. Miles of wiring were run, hydraulic lines installed, equipment mounts fitted. This allowed dozens of teams to work in parallel, without getting in each other's way. And then these ready-made sections, packed with internal modules, looking like giant chunks of an aluminum construction set, got wheeled over to the main assembly line. This was the climax, a line a mile long. At the start, there's just the center wing section. Then 2 fuselage halves get joined to it. The whole structure moves freely forward. At the next station, they attach the nose and tail sections. Further down, they mount the massive wings. And so, step by step, right before your eyes, from separate pieces, a gigantic, nearly 100-foot aircraft takes shape. At the final stations, they install 4 powerful Wright Cyclone engines, each churning out 1,200 horsepower, mount the landing gear, glaze the cockpit, and of course, fit its main argument. 13 heavy-caliber Browning M2 machine guns, which gave it the name Flying Fortress. At peak production, in 1944, the Willow Run plant rolled out 1 B-17 bomber every 63 minutes. Just think about that. Every hour, 24 hours a day, a brand new, battle-ready heavy bomber rolled through those factory gates. It was a non-stop river of steel, aluminum, and firepower. In total, during the war years, 3 companies, Boeing, Douglas, and Ford, built over 12,700 flying fortresses. This wasn't just a victory of technology, this was a victory of logistics, organization, and most importantly, people. 1.5 million ordinary Americans who put aside their peacetime lives and became soldiers on the industrial front. They proved that a free nation, when united by a common paycheck, is capable of genuine miracles. That was the arsenal of democracy in action. Thanks for watching. Hit that like button, subscribe, and see you next time. So, I know North Carolina doesn't sound particularly exotic, but what's being made here flies at 66,000 feet above the Pacific Ocean and keeps 400 passengers in the air at the same time. This is the factory that produces blades for the GE9X turbine engine series, the largest commercial jet engines in the world today. One of these engines weighs about 9 tons, generates thrust up to 105,000 pounds. Sorry, that's roughly 460 kilonewtons, and costs around $50 million. But we're not here because of the engine. We're here because of one specific part that's about the size of your palm and costs more than a nice car. A turbine blade. In the hot section of the engine, in what's called the high-pressure turbine, there are between 160 and 180 of them per wheel, depending on the stage. Each one weighs roughly 10.5 to 14 ounces. But the conditions it operates in, this isn't engineering anymore. It's straight-up torture for common sense. The temperature of the gases flowing around the blade during engine operation, 2,700 to 2,900 degrees Fahrenheit. That's higher than the melting point of steel, higher than the melting point of the very material the blade is made from. How it doesn't just melt, I'll tell you in a minute, because it's one of the coolest things I saw at this facility. The blade material is a nickel-based superalloy. The exact recipe is classified, and they didn't tell me the full breakdown, which is fair. But the general principle is known. Each element is responsible for something specific. Take rhenium, for instance. It provides heat resistance and slows down creep. That's when metal under prolonged stress and temperature deforms completely. The raw material cost for a single blade runs from 200 to 300 euros just for the metal, before anyone's even touched it. Now, how it all begins. The blade manufacturing process is investment casting, also known in the industry as lost wax casting. First step, the wax model. An exact replica of the future blade, including all internal channels, is created from wax under pressure in a metal mold. The precision of this mold, plus or minus 20 micrometers. That's about 1/4 of the thickness of a human hair. If the mold deviates any more than that, it goes back for refinement. But the wax model is just the outer form. Inside the blade, there are also cooling channels, thin, winding tunnels through which cold air from the compressor gets pumped during engine operation. That's why the blade doesn't melt, even though the surrounding gas is hotter than its own melting point. Inside, air at temperatures of 500 to 600 degrees Celsius flows through and keeps the metal in the working zone. These channels are formed separately, using ceramic cores that get inserted into the wax model before casting. The core looks like a thin, sturdy comb, and it occupies exactly the space where the channel will eventually be. The wall thickness between the blade's outer contour and the internal channel ranges from 1 to 2 millimeters. Any thinner, and the blade becomes brittle. Any thicker, and the cooling can't keep up. Next, the wax model gets dipped into a liquid ceramic slurry and coated with fine ceramic sand. Dip, pull out, dry, and repeat the cycle 8 to 12 times. Each layer dries for 4 to 8 hours. After the final layer, you get a ceramic blob about 10 millimeters thick, hard, rough to the touch, kind of like papier-mâché if papier-mâché were made from space shuttle material. Then this whole thing, with the wax still inside, goes into an autoclave, where at temperatures around 300 degrees Fahrenheit and elevated pressure, the wax melts out through a small opening. Hence the name, lost wax casting. What's left inside is a perfect negative of the blade shape. The ceramic holds its form, the cores stay in place. Now comes the metal pour. This is the part I came for. The molten metal gets heated to around 2500 to 2700 degrees Fahrenheit and poured into the ceramic mold. But they don't just pour it and wait for it to solidify. The mold gets slowly withdrawn from the heating chamber at a rate of about 1/10 to 1/5 of an inch per minute. That withdrawal speed controls how the metal crystallizes. If everything's done right, the entire blade, from root to tip, becomes a single crystal. Not a single grain boundary throughout the entire volume of metal. That's single crystal casting. Grain boundaries, the weakest spot in any metal. That's where cracks start under prolonged stress and heat. If there's only one grain, there's no boundary, no failure points. Heat resistance jumps roughly 30% compared to ordinary polycrystalline casting. After cooling, they break the ceramic shell, just mechanically, with hammers and vibration. Out comes a gray blade with ceramic cores inside. The cores come out in an alkaline solution at roughly 210 degrees. The chemistry dissolves ceramic, but leaves the metal untouched. This takes 4 to 8 hours. After washing, those same cooling channels remain in the center, clean, precise, completely open. Then they check the blade. X-rays reveal pores and cracks inside the metal. Fluorescent liquid catches surface defects. A special probe passes through each cooling channel, verifying it's not blocked by ceramic residue. If even one cooling channel is partially blocked, the blade goes straight to scrap. Not to rework, straight to scrap. Because you can't fix that. The rejection rate at this stage runs 2 to 5% per batch. Doesn't sound like much, but given what each part costs, we're talking real money. After inspection, heat treatment. The blade goes through multiple temperature cycles. First, around 1900 degrees for several hours, then a gradual cool down. This process evens out the internal stresses that formed during casting and locks in the alloy's microstructure. The exact heat treatment protocol? Also classified. When I asked, the manager who was walking me through just smiled and changed the subject. Final stage, protective coatings. First comes a metallic bond coat, nickel and aluminum based, applied using a plasma spray process. That's the foundation. On top of that goes the thermal barrier coating, zirconia stabilized with yttrium. It's ceramic. And it's that ceramic layer that absorbs the first several hundred degrees from the screaming hot gas stream. This layer is between 100 and 2 micrometers thick. The application looks like spray painting in a chamber. The blade rotates, the plasma gun moves along it following a preset path. But the temperature of the plasma stream during application is around 18,000 degrees Fahrenheit. For comparison, the surface of the Sun is about 10,000 degrees. So the tool is nearly twice as hot as a star, but the blade itself doesn't heat up more than 4 degrees because the entire process is incredibly fast and incredibly precisely controlled. The finished blade goes for final weighing, measurement, and registration. Each one gets an individual serial number and a passport where all parameters are recorded, from the chemical composition of the melt to the results of every control measurement. This document is kept for as long as the engine lives, and that's 20 to 30 years and tens of thousands of flight hours. On my way out, I asked how many blades they made per month. They told me it was in the range of several thousand units across all sizes. They wouldn't give me an exact number. But when you consider that one engine needs several hundred hot section blades alone, and orders for the 9X remain backed up for years ahead, you can imagine the scale. You're the best. Subscribe so you don't miss the next facility. It's going to be even more interesting. Write in the comments where you're from, and maybe next time I'll visit your city. Every year, millions of tons of metal waste get recycled worldwide, but only at the very end of this massive process does a substance emerge that's heavier than almost anything you've ever held in your hands. Picture a metal where a tiny piece weighs as much as a brick, and extracting it is more like hunting ghosts through fire and acid. Today, we're stepping inside a facility where one of the rarest and most mysterious metals on the planet is born from dirty sludge: osmium. But the most shocking part isn't its weight. It's what you have to go through to get even one small bar. And trust me, if you stick around until the end of this video, you'll learn a fact about this metal that literally breaks logic and makes you question the laws of physics. We're now entering the primary processing facility for platinum sludges. Everything around here is humming, steam's bursting out from under valves, and the workers look like they're gearing up for a flight to another galaxy based on the sheer amount of protective gear they're wearing. And that's no surprise. Osmium is basically the heavyweight champion of the periodic table, and it doesn't tolerate amateurs. It's twice as dense as lead. Just think about that for a second. If you grab a cube of this metal with sides only 4 inches long, it'll weigh nearly 22 pounds. That's like trying to pick up a full-grown cat that's compressed itself down to the size of a matchbox. The process of extracting osmium is a real adventure for anyone who loves complex flowcharts and intellectual challenges. This metal doesn't just lie around in proud nuggets deep in the earth, waiting for some lucky prospector to pick it up and slip it into their pocket. Nope, it's way trickier than that, and hides itself in the residues left over from the industrial purification of copper and nickel. Picture a whole mountain of rock that's already been processed, squeezed for everything possible, and only at the very end, in the dirty sludge, this heavyweight remains. You and I walk past massive vats where all hell breaks loose because the metal mixture gets hit with aggressive chlorine and insanely high temperatures. It looks like a set from a movie about the future, where humanity learned to extract value from dust. The work starts with anode slime. That's the sediment left over after electrolysis. To get to the osmium, specialists have to literally dismantle the molecular structure of this waste. First, the slime gets treated with acids to wash out the more cooperative metals. When it's our hero's turn, thermal processing kicks in. Temperatures here reach thousands of degrees Fahrenheit. This isn't just heating, it's total transformation of matter under the watch of dozens of sensors. When the mixture hits the reactors with chlorine, the most critical stage begins. Osmium reacts and transforms into a volatile compound. This gas needs to be captured with pharmaceutical precision. The slightest error in pressure or temperature, and the precious metal simply flies up the stack, leaving behind nothing but a foul smell. Special absorption towers step by step pull the gas in, converting it into a solution. It's like hunting a ghost, except instead of traps, you're using complex chemical filters. Next, the solution goes through several more purification stages until finally a precipitate appears, pure osmium salt. But that's still not the end of the road. This salt gets roasted again in a stream of hydrogen to produce that same dark blue powder. Every pound of this powder, That's the result of hundreds of workers and massive machines grinding away. Looking at these vats, you realize that osmium extraction isn't just metallurgy. It's the pinnacle of engineering genius, where every move costs thousands of dollars. This is work for the patient and the bold, because this metal doesn't forgive mistakes, but it rewards those who make it through all these fiery and chemical obstacles with its otherworldly strength. To extract it, you need to convert it into osmium tetroxide. And this is where the fun really begins, because this gas smells like someone decided to mix bleach with rotten radish and set it all on fire in a closed room. The metal's name actually comes from the Greek word meaning smell, and trust me, the Greeks knew what they were talking about. We move on to the separation laboratory. Here reigns an atmosphere of sterility that contrasts with the dirty rumble of the previous workshop. Scientists in white coats manipulate glass tubes and retorts. The whole process looks like a very expensive and dangerous cooking show. They extract osmium as a fine, dark blue powder. This powder looks beautiful, but it's incredibly treacherous. If you heat it in open air, it instantly becomes a toxic gas that can ruin not just your day, but your health for years to come. So airtightness is everything here. Look at these furnaces. They operate at temperatures that are hard to fathom, over 5,000 degrees Fahrenheit. That's way hotter than the surface of some stars. Because osmium has an incredibly high melting point, you can't just melt it in a bucket and pour it into molds. They use powder metallurgy methods here. The powder gets pressed under gigantic pressure, then sintered in a vacuum. What you get is like a metal sandwich that then becomes a monolith. It's fascinating to watch them try to cut this metal. Regular saws and drills are useless here. They just dull or snap like they're made of chocolate. Osmium is so hard and brittle at the same time that you can only work with it using lasers or supersonic water jets with added abrasives. It's a real challenge for engineers. Every disc or sphere produced costs a small fortune, because making a single part burns as much energy as a small town uses over a weekend. Why even bother with such a finicky material, you might ask? Well, besides looking like a chunk of frozen blue sky, it's incredibly wear resistant. It's used where you need something eternal, in high voltage switch contacts or in the tips of very expensive fountain pens used to sign peace treaties. This is one of those cases where quality justifies every cent spent and every whiff of that weird smell of ozone and chemistry. I'm standing next to a finished ingot. It's small, about the size of my palm. But when I try to move it, my muscles tense up like I'm pushing a small car. This little guy weighs about 35 pounds. You can't capture this feeling through a camera. It violates every law of logic we're used to in everyday life. You expect lightness, and you get a gravitational punch to your arms. Now we're moving into the packaging zone. Even here, everything's serious. Every gram is accounted for. Every ingot has its own certificate and number. This isn't the kind of metal you accidentally forget in your work jacket pocket. Its market price swings so wildly that investors sometimes drink more sedatives than coffee. But demand for this blue shimmer keeps growing because the world's getting more technological, and osmium, it's exactly the ingredient that makes modern electronics reliable. You know what struck me most at this plant? It's the people. They talk about this metal like it's a living creature with a really bad temper, one they've learned to respect and tame just a little. There's no room for rushing here. Every move is calculated to the inch. Every second in the furnace is accounted for. This isn't just manufacturing. It's a battle of human intellect against the physical limits of matter. We're wrapping up our tour at the finished product display. Here you'll find small parts that'll soon ship all over the world. Some will end up in spacecraft, others will become part of medical devices. And every time you hear about something incredibly strong and durable, remember this blue, smelly, and impossibly heavy metal. Hope you enjoyed this walk along the edge of the periodic table. It was tough in every sense of the word. Don't forget, the world around us is way more interesting than it seems at first glance, especially if you peek behind the fence of a big factory. It was fun showing you this metallic extreme. Until next time at new facilities, where we'll definitely find something else that'll make your eyebrows shoot straight up in surprise. Did you enjoy this format? Maybe you'd like me to prepare a detailed script about manufacturing another rare metal, or talk about the logistics of moving these heavy ingots around. Every year, billions of bolts get manufactured worldwide, so many that you could wrap them around the Earth thousands of times. But hidden in that ocean of metal, there are a select few that cost hundreds of dollars apiece, and literally have lives depending on them. Today, I'm taking you to a place where an ordinary bolt transforms into something far greater. A component that withstands extreme temperatures, crushing pressure, and even the vacuum of space. There's no factory noise here, but there is something else. Something they don't talk about openly. And if you stick around till the end, you'll understand why a $500 price tag is just the tip of the iceberg. The first thing that hits you right when you walk in? Silence. For some reason, I was expecting noise, like you'd get in a regular machine shop. But here, everything's calm. A few machines, 3 or 4 operators, and this feeling like you didn't just walk into a factory, you walked into a lab. Actually, that's exactly what it is. A lab. That also happens to be a factory. Let me walk you through how every bolt begins. The raw material is a specific nickel-chromium alloy that has to be ordered ahead of time and arrives in rods about 3/4 of an inch in diameter. One of those rods weighs around 20 pounds. It costs roughly $250, and that's before anyone's even touched it. The material isn't chosen randomly. It can withstand temperatures up to 2,000 degrees Fahrenheit, won't deform under pressure of 150,000 pounds per square inch. And here's the kicker. It doesn't lose toughness, meaning it won't go brittle like glass. A regular semi rumbles down the highway. Nothing special, no markings whatsoever. Thousands just like it roll through Connecticut every day. Inside, on wooden pallets bound with metal straps, lie the rods. Not dumped in a heap, not just thrown together, each layer separated by wooden spacers so the rods don't touch or scratch each other. Because a scratch on the raw material surface is already a detected defect that later gets damaged or cut away. One pallet, typically 40 to 60 rods, depending on length. A pallet like that weighs around 1,200 pounds. The truck can carry 6 to 8 of these pallets, meaning one trip hauls roughly $80,000 worth of material. Yet the truck itself looks no different from one hauling pens to a supermarket. At the factory, the truck backs into the loading dock, a small bay with a single door, sized specifically for one trailer. The driver backs up, the dock locks click into place, and then the forklift takes over. The operator grabs the pallet, hauls it to the raw material warehouse, a separate room with controlled temperature and humidity, because the alloy can't pick up moisture before processing. There, each pallet gets a paper tag with the batch number, delivery date, and material certificate, a document from the supplier listing the exact chemical composition of that specific melt. Without that certificate, the bars don't even make it into the plant. The driver can wait at the gate all day. And this is where things get interesting. The stuff you don't see from the outside. Before a bar hits the machine, they cut off a small chunk, about an inch long, and send it to the in-house lab for incoming inspection. They check hardness, examine the structure under a microscope, sometimes run a spectral analysis. Takes 2 to 4 hours. Only after the lab gives the green light does the batch get accepted and move into production. If the result doesn't match the certificate, they return everything, even if the difference is minimal. They cut a blank from the bar stock. A CNC machine removes material layer by layer. One blank is roughly 4 inches long. Cutting takes about 20 minutes per piece, and during that time, the machine makes approximately 2,000 individual movements with different tools. The chips that remain get collected. They're worth money too. Next, heat treatment. The blank goes into a furnace and holds at 1750 degrees Fahrenheit for 4 hours. This is what's called annealing, a process that relieves internal stress in the metal that built up during cutting. Skip this step, and the bolt can have micro cracks invisible to the naked eye, but under load, they become a big problem. After the furnace, the blank gets cooled down, not in cold water, not in open air, but in specialized chambers with a controlled atmosphere where the temperature drops at a rate of 50 degrees per hour. The entire cooling cycle? That's another 8 hours. Now here's where it gets interesting. Thread cutting. The threads on these bolts aren't standard. They're engineered for a specific application, and in some cases are the customer's own proprietary design. The thread pitch might be, say, 28 threads per inch. That's an extremely fine pitch, ensuring maximum load distributed across the entire length of contact. Thread cutting is done on that same CNC machine, but now with a different tool, a carbide-coated threading tap. Cutting speed here is super low, around 30 revolutions per minute. Nothing gets rushed here. After the threads are cut, every bolt gets checked with a thread gauge. If the gauge goes in with the right amount of force, good. If it's too easy or too tight, the bolt goes back for rework or gets scrapped. If a bolt fails inspection, they don't try to fix it. They just start making a new one. Next up, final mechanical finishing. That's polishing the seating surfaces. Under the bolt head, there's a ring zone about 3/60ths of an inch wide that gets smoothed down to a surface roughness of 2 micro-inches. That's 50 times thinner than a human hair. For comparison, your average bolt from the hardware store has a roughness anywhere from 100 to 200 micro-inches, and nobody bats an eye. But here, this zone carries contact stress after the bolt gets tightened, and if it's uneven, microscopic movement can start. Fretting, as engineers call it. And over time, the bolt will loosen. Can you imagine? Such massive work, but it's like jewelry. The coating is a whole separate deal. The entire bolt gets a nickel coating, 1 to 2 thousandths of an inch thick, through electrodeposition. Parts get dunked in a solution bath, and a direct current runs through it. Nickel gradually settles onto the surface in an even layer, about 20 millionths of an inch per year. The whole procedure takes 3 to 6 years, depending on the thickness required. After that, they check it, measuring thickness with an ultrasonic probe at 2 to 4 points across the bolt's surface. If there's more than a 10% deviation anywhere from spec, the bolt goes back for recoating. Now, where do these bolts actually go? Aviation is one of the main buyers, engine and landing gear fasteners. Then there are submersibles, where threaded connections have to handle pressure at depths of several thousand feet without corroding. There are clients from the nuclear industry. And there are a few projects in the space sector the factory doesn't really want to talk about. They just say, limited disclosure contract, and smile. When I asked how many bolts they make per day, the answer surprised me. 20 to 50 pieces. That's it. The factory doesn't chase productivity records, but each bolt passes through an operator's hands at least 7 times during the production cycle, which takes a total of 3 to 5 working days. Some bolts take a week to make, if the customer wants X-ray inspection and fatigue testing on top. That's a separate procedure. They load the bolt cyclically, 100,000 tension and compression cycles, watching for any cracks. I asked one of the operators if this all seemed like overkill for a bolt. He looked at me without much emotion and said, "This isn't a bolt. It's a system component whose failure costs more than our entire factory." Short and to the point. So there's your $500 a piece. And after that tour, I don't think it's expensive anymore. You're the best. Subscribe so you don't miss the next factory. It's gonna be even more interesting. Drop a comment saying where you're from, and maybe next time I'll swing by your state. Every year, machines are built around the world so massive and powerful that a single one could supply electricity to an entire city, and costs as much as dozens of private jets. But what if I told you that inside this colossal structure, there are parts machined with precision, thinner than a human hair, and that one tiny mistake could cost millions of dollars or even destroy everything? Today we're going inside a place almost no one gets to see, the heart of turbine manufacturing. And trust me, What you're about to see will completely change how you think about engineering, if you stick around till the end. Let's start with the fact that there are two main types of these turbines, and they work on very different principles. First, the steam turbine. You'll find these at nuclear and thermal power plants, on massive tankers and icebreakers. Second, the gas turbine. It's more like a giant jet engine without wings and lives mostly at gas-fired power plants and on some military vessels. Here at the factory they make both types, but we're heading first to the steam ones because they're older, more massive, and look like they were invented 2 centuries ago. Which, actually, they were, but they're still very much around. How a steam turbine works: short and formula-free. There's a boiler that heats water into pressurized steam at anywhere from 800 to 3,000 pounds per square inch. This steam, hot, pressurized, angry, blasts through nozzles onto rotor blades. The blades start spinning. The rotor spins the shaft. The shaft spins a generator or a ship's propeller. The steam cools down, condenses back into water, and returns to the boiler. The cycle is closed. Sounds simple, but for this simple not to explode into pieces and to run for 3 years without major repairs, you need all of this around me. The first shop they take me to is the foundry. This is where every turbine begins. The casing, the outer shell that holds all the internal components under pressure, is cast from alloy steel or cast iron, depending on operating parameters. For steam turbines in large power plants, the casing is cast in 2 or 3 tiers, and each tier is a separate mold. The mass of 1/2 of a casing can reach 60 to 80 tons. The metal is melted in arc furnaces with a capacity of 50 to 150 tons of molten metal, and the temperature there is around 5,000 degrees Fahrenheit. The mold for a large casing is a pit in the floor, 6 to 10 feet deep, lined with refractory clay. The metal is poured through a system of channels, and the entire process of filling one large mold takes 15 to 30 minutes. Then the casting cools, naturally from several days to 2 weeks, depending on the mass. After cooling, the casting goes to its first inspection. Ultrasonic testing searches for voids and inclusions inside, spots where the metal didn't fuse the way it should. X-rays check critical zones. If they find something significant, the casting goes back to remelt. No compromises. The rejection rate at this stage runs 3 to 8% depending on the casting's complexity, and that's completely normal for parts this size. Next, machining. Now, here in the shop floor, there are machines that made my jaw drop. The horizontal boring mill that machines the inner casing surface, it's about 60 feet long. The table where the part sits moves. The spindle stays put. The tool freely bores the bearing and seal mounting surfaces to an accuracy of plus or minus 0.5 of an inch. Why so precise? Because the rotor spinning inside at 1500 to 3600 revolutions per minute has a clearance between its blades and the casing of 50 to 150 micro-inches. 1% efficiency loss at a large power plant. That's millions of dollars in extra fuel costs per year. The rotor is the star of this story. It's a shaft carrying discs with blades, and it's the most complex part of the entire turbine. The shaft for a large steam turbine is a forging made from special chromium molybdenum vanadium steel, 20 to 40 feet long and weighing 20 to 60 tons in its rough state. A forging means you take a red-hot ingot of metal and just hammer it with a press weighing 5,000 to 50,000 tons to give it the shape you need. The grain structure of the metal during forging gets oriented along the shaft's axis. That's how you achieve torsional strength. After forging, the shaft goes through heat treatment again, then heads to the machine shop. Turning takes 2 to 4 weeks of continuous work on a lathe that's nearly 70 feet long. Chips fly, coolant flows, and machining away from that massive blank reveals the sleek shaft you saw in the drawings. This is the part where I'm always amazed. A gigantic component, yet precision like a watch mechanism. Blades are a separate production line. Steam turbines at large power plants have anywhere from 8 to 20 stages, and each stage is a disc with blades. First stage blades are small, sometimes less than 2 inches tall, because the steam there is still under high pressure and dense. Last stage blades are massive, up to 5 or 6 feet long on the largest turbines. These blades are forged and milled from iron-based alloys or stainless steel, and in their final profile, they have an aerodynamic shape with precision to within plus or minus 0.002 of an inch along the entire length. Each blade is checked for resonant frequency. It can't match the operating rotational frequency of the rotor, or else after a few thousand hours, a fatigue crack will develop from vibration. How they test this is simple. They tap the blade with a small hammer and listen with a special acoustic sensor. A very elegant method for such a serious problem. Assembling the rotor. This is when it starts to feel like an operating room. Bladed discs get mounted onto the shaft using shrink fitting. The disc gets heated to 300 to 400 degrees Fahrenheit. It expands, slides onto the shaft, then cools and grips the shaft with a force no bolt could ever match. No threads, no glue, just temperature difference and precision sizing. The interference fit when cold, 1 to 3 thousandths of an inch per inch of diameter. After assembly, the rotor gets balanced, and this takes 1 to 3 days. Balancing happens on a specialized rig, where the shaft spins on bearings while sensors register vibration. If there's any imbalance, metal gets removed from certain spots, or balancing inserts get installed. Allowable residual vibration on a large rotor, fractions of an ounce per inch of radius. If you think that's strict, you're thinking right. After assembly, the turbine heads to the test stand. At full operating parameters, pressure and temperature, they run the turbine for 24 to 72 hours. Sensors track bearing temperatures, vibration, steam leaks, power output. If anything goes outside the limits, stop, disassemble, analyze. There have been cases where they found a defect here that the X-ray missed initially. So the test stand isn't just a formality. It's the last line of defense before shipping. The finished turbine gets broken down into transport blocks, casing separate, rotor separate, auxiliary equipment separate. A large turbine rotor travels on a special trailer with hydraulic suspension, the kind you've seen on YouTube, with 18 axles moving at 20 miles per year. They coordinate the route a month in advance. Every bridge height and every turn width needs checking from the factory to the port or customer. Sometimes for one of these transports, they temporarily remove road signs and even take down power lines over the highway. I asked the chief engineer how many turbines they build per year. He said 12 to 20 of various types. That's it. Less than 2 per month. But each one runs for 30 to 50 years and generates electricity for hundreds of thousands of people every day. Some things don't need high volume production. Can metal burn brighter than the sun? Sounds impossible. But one element does this every day, and we're about to touch its mystery right now. Imagine a material lighter than plastic, yet capable of withstanding loads that break steel. A material hidden in seawater, in stone, in the technology around us, but the way it's extracted looks more like alchemy than industry. And here's the thing. By the end of this video, you'll learn about a property of magnesium that even many engineers have never heard of. Ready to discover what giant furnaces, seawater, and 1,000-degree flames have been hiding? Magnesium is often called the metal that defies intuition. It's lighter than many types of plastic, weighing approximately 0.063 pounds per cubic inch, 1.5 times lighter than aluminum, and nearly 4 times lighter than steel. In your hands, it feels almost hollow inside. Yet this metal demonstrates remarkable strength in alloys and can withstand loads its mass simply doesn't suggest. What's most striking is how it burns. Given sufficient temperature, magnesium produces light so intense that its brightness reaches close to 3,500 degrees Fahrenheit, and watching the flame without protection is impossible. That's precisely why magnesium flashes were once used in photography and pyrotechnics. During combustion, it forms white smoke of magnesium oxide, and the flame itself looks as if someone turned on a concentrated beam of sunlight. In nature, pure magnesium doesn't exist. It's bound up in minerals, and the two main sources are dolomite and seawater. Global estimates suggest that the oceans contain over 1.3 quadrillion tons of magnesium, making it one of the most abundant metals in a form accessible to humanity. However, extracting it from water is a complex and energy-intensive process. Picture an industrial facility on the coast where the sea is essentially raw material. Everything runs continuously through a system of powerful pumps. Pipelines stretch from the shore to the processing units, moving thousands of gallons per hour. The water flows into large open or enclosed basins resembling giant reservoirs, where it's filtered for the first time to remove debris, sand, and biological contaminants. After that, in similar tanks, a calcium hydroxide slurry is added. This happens through automated dispensers that feed the material into the water, so the reaction proceeds evenly. From the outside, it looks like a slow transformation of transparent seawater into a cloudy liquid, as if someone added fine white powder that gradually binds the dissolved magnesium into flakes of sediment. While the reaction continues, large mixers move through the pool, sometimes resembling windmill blades, only turned horizontally. They stir the liquid almost silently, so the sediment forms everywhere rather than clumping together in one spot. When the particles become heavier and start settling to the bottom, the liquid is pumped into the next settling tank. There it sits for several hours, and the solid fraction slowly settles, forming a dense layer that looks like wet cement. The upper part of the water is drained back into the sea or directed for retreatment, while the sediment is collected by special grabs or vacuum systems. Then, the sediment is rinsed with fresh water and dried in powerful drying ovens that blow hot air at speeds capable of removing an entire layer of moisture in a minute. When the mass becomes brittle, it's moved to roasting furnaces. Inside, temperatures exceed 1,380 degrees Fahrenheit, and the material gradually transforms into magnesium oxide. From the outside, it looks like an endless white ribbon of powder, being fed by conveyor into the scorching chambers and emerging with a completely different structure. The final stage is electrolysis. The oxide enters sealed high-temperature chambers where it's mixed with salt flux. This happens either in smelting vats or in special crucibles, where the material gradually transforms into a thick, molten mass. The metal chamber walls glow red from the heat, and inside, the molten material looks like incredibly thick, scorching soup. At this point, electric current passes through it. You can only watch through protective windows, because everything inside appears to glow. Magnesium begins separating into tiny droplets that rise to the surface, since their density is lower than the molten mixture. It's collected using special ladles or drainage systems, and eventually the metal accumulates as shiny silver ingots, ready for further purification or casting into molds. In the case of dolomite, everything starts at the quarry, where the rock lies in massive layers. Extraction doesn't look like romantic stone chipping. It's the work of giant excavators, drilling machines, and blasting equipment. First, the rock gets crushed right on site. Massive jaw crushers chew through refrigerator-sized chunks and turn them into material that can move along conveyor belts. From there, the dolomite heads to factory hoppers, where machines precisely meter the flow and feed it into calcination kilns. The kilns work like giant tubes heated to 1,650 degrees. Inside, the dolomite slowly descends, while hot air, fed from below, passes through the entire layer of material. From the outside, you only see bright bands of glowing metal, but inside, something crucial happens. The dolomite breaks down into magnesium oxide and calcium oxide. After leaving the kiln, the hot mass travels along metal chutes and cools under powerful blasts of air. Next comes the stage where dolomite transforms into something resembling factory architecture. A tall tower with vessels, pipes, and tanks. Coke, or ferrosilicon, is fed into this tower, along with pre-crushed calcined dolomite. This mixing happens in specialized reactors that look like enormous drums, slowly rotating to ensure uniform contact between reagents. Everything appears as a continuous flow of dry, grayish powder sliding into the reduction furnace. Inside the furnace, the temperature climbs even higher, over 2,550 degrees. The heat inside is so intense that everything around glows with a dim red light. Under these conditions, magnesium oxide reacts with the reducing agent, and the metal transitions into vapor phase. This is one of the most distinctive features of magnesium production. The metal evaporates and rises through the furnace, while gaseous particles move into the condensation chamber. The chamber looks like a vertical steel cylinder with cooled walls from the outside. Inside, magnesium vapors meet the cold surface, and the metal condenses as a shiny coating that resembles silvery frost. This coating gets periodically scraped off by mechanical scrapers or robotic manipulators operating in an environment with minimal oxygen access. The collected metal goes into protected containers, where it's melted again to remove residual impurities. The melting crucibles look like deep wells filled with glowing silvery molten metal, and extraction systems constantly work above them, protecting the metal from contact with air. The process ends with casting into molds, where magnesium cools and transforms into ingots. Each ingot represents the end of a long journey, from stone extracted by explosions to metal that emerged through evaporation and condensation. Global magnesium production holds steady at around 1 million tons per year. China supplies roughly 85% of that volume, while the United States, Israel, and Kazakhstan handle the rest. Interest in the metal grows annually because the aerospace, automotive, and electronics industries are hunting for the lightest materials possible. For example, using magnesium alloys in transportation cuts component weight by 20 to 35% compared to aluminum. That reduces fuel consumption and boosts overall efficiency. In electronics, magnesium shows up in laptop casings, camera bodies, and smartphones. It's not just light, it also absorbs vibrations well and dissipates heat effectively. In the United States, the share of magnesium in automotive parts has climbed from 3 pounds per vehicle 20 years ago to over 12 pounds in current models, and that figure keeps rising. Despite magnesium being lightweight, flammable, and extremely reactive, it's incredibly difficult to replace. It has a rare combination of mass, strength, and reactive properties that make it one of the most important structural metals of our time. And even though humanity has been producing it for only a century, the potential for its use hasn't come close to being exhausted. If current trends in aviation and electric vehicles continue, analysts predict global demand will reach 2 million tons within a decade. Can metal burn brighter than the sun? Sounds impossible. But one element does this every day, and we're about to touch its mystery right now. Imagine a material lighter than plastic, yet capable of withstanding loads that break steel. A material hidden in seawater, in stone, in the technology around us, but the way it's extracted looks more like alchemy than industry. And here's the thing. By the end of this video, you'll learn about a property of magnesium that even many engineers have never heard of. Ready to discover what giant furnaces, seawater, and 1,000-degree flames have been hiding? Magnesium is often called the metal that defies intuition. It's lighter than many types of plastic, weighing approximately 0.063 pounds per cubic inch, 1.5 times lighter than aluminum, and nearly 4 times lighter than steel. In your hands, it feels almost hollow inside, yet this metal demonstrates remarkable strength in alloys and can withstand loads its mass simply doesn't suggest. What's most striking is how it burns. Given sufficient temperature, magnesium produces light so intense that its brightness reaches close to 3,500 degrees Fahrenheit, and watching the flame without protection is impossible. That's precisely why magnesium flashes were once used in photography and pyrotechnics. During combustion, it forms white smoke of magnesium oxide, and the flame itself looks as if someone turned on a concentrated beam of sunlight. In nature, pure magnesium doesn't exist. It's bound up in minerals, and the two main sources are dolomite and seawater. Global estimates suggest that the oceans contain over 1.3 quadrillion tons of magnesium, making it one of the most abundant metals in a form accessible to humanity. However, Extracting it from water is a complex and energy-intensive process. Picture an industrial facility on the coast where the sea is essentially raw material. Everything runs continuously through a system of powerful pumps. Pipelines stretch from the shore to the processing units, moving thousands of gallons per hour. The water flows into large open or enclosed basins resembling giant reservoirs, where it's filtered for the first time to remove debris, sand, and biological contaminants. After that, in similar tanks, a calcium hydroxide slurry is added. This happens through automated dispensers that feed the material into the water, so the reaction proceeds evenly. From the outside, it looks like a slow transformation of transparent seawater into a cloudy liquid, as if someone added fine white powder that gradually binds the dissolved magnesium into flakes of sediment. While the reaction continues, large mixers move through the pool, sometimes resembling windmill blades, only turned horizontally. They stir the liquid almost silently, so the sediment forms everywhere rather than clumping together in one spot. When the particles become heavier and start settling to the bottom, the liquid is pumped into the next settling tank. There it sits for several hours, and the solid fraction slowly settles, forming a dense layer that looks like wet cement. The upper part of the water is drained back into the sea or directed for retreatment, while the sediment is collected by special grabs or vacuum systems. Then, the sediment is rinsed with fresh water and dried in powerful drying ovens that blow hot air at speeds capable of removing an entire layer of moisture in a minute. When the mass becomes brittle, it's moved to roasting furnaces. Inside, temperatures exceed 1,380 degrees Fahrenheit, and the material gradually transforms into magnesium oxide. From the outside, it looks like an endless white ribbon of powder, being fed by conveyor into the scorching chambers and emerging with a completely different structure. The final stage is electrolysis. The oxide enters sealed high-temperature chambers where it's mixed with salt flux. This happens either in smelting vats or in special crucibles, where the material gradually transforms into a thick, molten mass. The metal chamber walls glow red from the heat, and inside, the molten material looks like incredibly thick, scorching soup. At this point, electric current passes through it. You can only watch through protective windows, because everything inside appears to glow. Magnesium begins separating into tiny droplets that rise to the surface, since their density is lower than the molten mixture. It's collected using special ladles or drainage systems, and eventually the metal accumulates as shiny silver ingots, ready for further purification or casting into molds. In the case of dolomite, everything starts at the quarry, where the rock lies in massive layers. Extraction doesn't look like romantic stone chipping. It's the work of giant excavators, drilling machines, and blasting equipment. First, the rock gets crushed right on site. Massive jaw crushers chew through refrigerator-sized chunks and turn them into material that can move along conveyor belts. From there, the dolomite heads to factory hoppers, where machines precisely meter the flow and feed it into calcination kilns. The kilns work like giant tubes heated to 1,650 degrees. Inside, the dolomite slowly descends, while hot air, fed from below, passes through the entire layer of material. From the outside, you only see bright bands of glowing metal, but inside, something crucial happens. The dolomite breaks down into magnesium oxide and calcium oxide. After leaving the kiln, the hot mass travels along metal chutes and cools under powerful blasts of air. Next comes the stage where dolomite transforms into something resembling factory architecture. A tall tower with vessels, pipes, and tanks. Coke, or ferrosilicon, is fed into this tower, along with pre-crushed calcined dolomite. This mixing happens in specialized reactors that look like enormous drums, slowly rotating to ensure uniform contact between reagents. Everything appears as a continuous flow of dry, grayish powder sliding into the reduction furnace. Inside the furnace, the temperature climbs even higher, over 2,550 degrees. The heat inside is so intense that everything around glows with a dim red light. Under these conditions, magnesium oxide reacts with the reducing agent, and the metal transitions into vapor phase. This is one of the most distinctive features of magnesium production. The metal evaporates and rises through the furnace, while gaseous particles move into the condensation chamber. The chamber looks like a vertical steel cylinder with cooled walls from the outside. Inside, magnesium vapors meet the cold surface, and the metal condenses as a shiny coating that resembles silvery frost. This coating gets periodically scraped off by mechanical scrapers or robotic manipulators operating in an environment with minimal oxygen access. The collected metal goes into protected containers, where it's melted again to remove residual impurities. The melting crucibles look like deep wells filled with glowing silvery molten metal, and extraction systems constantly work above them, protecting the metal from contact with air. The process ends with casting into molds, where magnesium cools and transforms into ingots. Each ingot represents the end of a long journey, from stone extracted by explosions to metal that emerged through evaporation and condensation. Global magnesium production holds steady at around 1 million tons per year. China supplies roughly 85% of that volume, while the United States, Israel, and Kazakhstan handle the rest. Interest in the metal grows annually because the aerospace, automotive, and electronics industries are hunting for the lightest materials possible. For example, using magnesium alloys in transportation cuts component weight by 20 to 35% compared to aluminum. That reduces fuel consumption and boosts overall efficiency. In electronics, magnesium shows up in laptop casings, camera bodies, and smartphones. It's not just light, it also absorbs vibrations well and dissipates heat effectively. In the United States, the share of magnesium in automotive parts has climbed from 3 pounds per vehicle 20 years ago to over 12 pounds in current models, and that figure keeps rising. Despite magnesium being lightweight, flammable, and extremely reactive, it's incredibly difficult to replace. It has a rare combination of mass, strength, and reactive properties that make it one of the most important structural metals of our time. And even though humanity has been producing it for only a century, the potential for its use hasn't come close to being exhausted. If current trends in aviation and electric vehicles continue, analysts predict global demand will reach 2 million tons within a decade. What if I told you that a high-speed train wheel experiences temperatures hot enough to make metal glow, and still can't afford to fail? Why must this piece of steel withstand tests that would destroy any car wheel in seconds? There's a reason almost nobody suspects, and if you stay with me through to the finale, you'll discover the secret process that forces the wheel to survive where other metal simply melts. But first, tell me, does your country actually manufacture railway wheels? Or are they imported? A train rockets down the tracks at over 186 miles per hour. At that speed, an ordinary wheel would simply disintegrate. Why? Because it has to withstand not just weight, but a whole series of inhuman trials. The material is everything. This isn't ordinary steel used for silverware or even car bodies. High-speed train wheels are made from a special grade of steel, melted according to a unique, meticulously refined recipe. This recipe is a combination of iron with specific alloying elements, manganese, silicon, chromium, molybdenum, that give the steel extraordinary strength, toughness, the ability to absorb impacts without failing, and endurance. Beyond that, this steel must be as pure as possible, free of any foreign impurities that could become a weak point. After the special steel is melted in massive metallurgical furnaces, it's poured into molds to create large steel billets, what we call slabs or blooms. But that's just the beginning. The real transformation starts in the forging shop. This is where one of the most powerful forging presses comes into play, along with specialized forging machines. The billet, heated until it glows bright yellow or red, that's around 2000 degrees Fahrenheit, is fed under the press. The process involves multi-stage forging. It's not a single strike, but rather a whole series of controlled pressures and rotations. The giant hammers, or jaws of the press, slowly, yet with unstoppable force, flatten and shape the red-hot metal. First stage, the billet is compressed to give it a rough circular shape, densifying the metal and eliminating internal voids. Second stage, the material is flattened and rolled, forming a disc with a central hole. This is where the future wheel's outline begins to emerge, with its rim, disc, and hub. This directional metal flow shapes its internal fibrous structure, making the wheel exceptionally strong in the required directions. Forging, unlike casting, transforms steel's microstructure. It compresses the metal's grains, eliminates casting defects, and creates a directional fibrous structure that gives the wheel exceptional strength and fatigue resistance. It's like an athlete's muscles. After training, they become stronger and more resilient. Why such complexity? Because high-speed train wheels operate under extreme conditions that are hard to imagine. When moving at speeds over 186 miles per hour, the wheel's surface heats up from friction against the rails and brake pads to nearly 2,000 degrees Fahrenheit. That's the temperature at which metal begins to glow red and change its properties. And this heating isn't constant, it's cyclical. Heating during acceleration and braking, cooling during movement. The material must withstand these constant temperature fluctuations without forming microcracks, which over time can lead to failure. Each pair of wheels carries a load of dozens of tons. A single railcar can weigh between 50 and 70 tons, and this weight is distributed across just 4 wheels, that is, 2 wheel sets. This creates constant pressure acting on the wheel. The train doesn't ride on a perfectly smooth surface. It crosses rail joints, uneven sections, and switches, which generate continuous impact loads. The wheel must be incredibly tough to absorb these shocks without cracking or breaking apart. After forging, the wheels aren't finished yet. They undergo complex heat treatment, which is key to developing their final properties. The wheel centers, the discs that connect the hub to the rim, are hardened. Hardening is a process of heating steel to high temperatures, then rapidly cooling it. This makes the metal harder and stronger. But hardening makes the metal brittle, so it's always followed by tempering, reheating to a lower temperature with slow cooling. Tempering reduces brittleness and improves toughness while maintaining high strength. This combination of hardening and tempering creates the ideal steel microstructure that can withstand extreme operating conditions. But even after all these complex processes, no wheel reaches the rails without brutal yet necessary testing. Every single wheel, without exception, undergoes ruthless inspections. Ultrasonic testing. It's like medical ultrasound diagnostics, but for metal. Special sensors send high-frequency ultrasonic waves through the wheel. If there's even a microscopic crack, void, or defect inside, the ultrasonic wave bounces off it and creates an echo that the instrument captures. This method allows us to see internal defects without destroying the wheels. A defect the thickness of a human hair is already grounds for rejection. Magnetic particle inspection. The wheel gets magnetized, then its surface is coated with fine ferromagnetic powder. If there's a crack, even one invisible to the naked eye, it distorts the magnetic field, and the powder concentrates along that crack, making it visible. This reveals even the tiniest surface defects that could become failure points during operation. Only wheels with perfect structure and 0 defects are cleared for installation on high-speed trains. This isn't engineering perfectionism. It's about the safety of thousands of passengers who trust their lives to these metal giants. While the United States isn't leading high-speed rail development like China or Japan, its rail network remains one of the world's largest, and American manufacturers have extensive experience producing high-quality wheels for various rolling stock, passenger trains, freight locomotives, and switching equipment alike. Unlike the automotive industry, where thousands of companies manufacture parts, the railroad wheel manufacturing market in the US is significantly more concentrated. This is a highly specialized field, requiring massive investments in metallurgical equipment, forging presses, and quality control systems. The two main and most powerful players in the North American railroad wheel manufacturing market are Amstead Rail and KF USA. While CAF is a Spanish company, it maintains production facilities in the United States to meet local demand. Previously, other major manufacturers existed, but the market has consolidated. Total annual railroad wheel production in the US fluctuates, but can be estimated in the range of 300,000 to 500,000 units per year. This figure includes wheels for all types of rolling stock. It's worth noting that while the US can manufacture wheels capable of withstanding high speeds, the actual demand for wheels designed for continuous operation above 186 miles per hour remains relatively limited due to the scarce number of true high-speed rail lines in the country. For instance, Amtrak's Acela Express trains, running along the Northeast Corridor, reach speeds up to 150 miles per hour on certain segments, but not beyond the aforementioned threshold of 186 miles per hour, which requires specific material and design standards. However, US wheel manufacturing technologies and standards do enable production that meets international requirements for high-speed trains should the need arise. From a material standpoint, American manufacturers, like their global counterparts, utilize specialized grades of carbon steel alloyed with manganese, silicon, and other elements to achieve the necessary strength, wear resistance, and toughness. Forging, heat treatment, and non-destructive testing processes are standard and comply with the highest international safety and quality benchmarks. You can find in ordinary dirt that contains so much energy, 2 pounds replaces 6 million pounds of coal. A rock you shouldn't touch with bare hands, controlled more strictly than gold, and determines whether entire cities have power in winter. This is uranium ore, the planet's most controversial geological resource, simultaneously saving us from climate catastrophe and threatening nuclear apocalypse. Let's dive into a world where geology collides with nuclear physics, and ordinary stone can change the fate of civilization. Let's start with what uranium ore actually looks like. If you're picturing something bright green, glowing in the dark like those mutant movies, I hate to break it to you. Most uranium ore looks like regular gray or yellowish brown rock, sometimes with a greenish tint, sometimes with black spots, but nothing particularly mind-blowing. You could walk right past this stuff in the mountains and never even know it's radioactive. True, there are minerals like uraninite or torbernite that have a brighter yellow-green color, but that's more the exception. Real glow happens, but not from the uranium itself. Some uranium minerals fluoresce under ultraviolet light. They light up bright green or yellow. Geologists use this to find deposits. They shine UV lamps in the dark, and the ore gives itself away with that glow. Looks straight up cosmic, especially in caves, where the walls suddenly burst into neon colors. But the main feature of uranium ore isn't its appearance, it's what's inside. Uranium-238 and uranium-235 are isotopes that slowly decay, releasing radioactive radiation for billions of years now. 1 gram of uranium emits around 12,000 radioactive particles per second. Not enough to kill you instantly, but enough to build up a dangerous dose over years if you constantly carried a rock like that in your pocket. Uranium is found everywhere, in rocks, soil, water, even seawater. The average concentration in Earth's crust is about 3 parts per million. That means in every ton of ordinary dirt, there's roughly 3 grams of uranium. But for industrial mining, you need concentrations at least 100 times higher, from 0.3% and up. Deposits like that are rare and only form under specific geological conditions. The richest deposits are found in Kazakhstan, Canada, Australia, Niger, and Namibia. Kazakhstan leads in production, about 45% of global output. Canadian deposits in the Athabasca Basin contain ore with uranium concentrations up to 20%. That's fantastically high. For comparison, most deposits have between 0.1 and 1%. How do you mine uranium ore? There are 2 main methods: traditional shaft mining and in-situ leaching, which sounds like something from a sci-fi movie but actually works. In the first case, you dig a mine or an open pit, blast the rock with explosives, load it onto dump trucks, and haul it to a processing plant. Just like any other ore, except with radiation. Miners work under special conditions. Constant radiation monitoring, dosimeters on every worker, limited time in high radiation zones. The air in the mines can contain radon, a radioactive gas released when uranium decays. It's constantly pumped out by powerful ventilation systems. Without this, miners would receive dangerous radiation doses in a matter of months. Now, about in situ leaching. Instead of digging a mine, they drill boreholes straight down to the ore deposit at depths of 300 or 600 feet. Through some boreholes, they pump in a solution, usually sulfuric acid with an oxidizer, or soda solution, depending on the type of ore. This solution dissolves the uranium right there underground. Through other boreholes, they pump out the solution that now contains dissolved uranium. At the surface, they extract the uranium from this solution using chemical methods. Underground leaching is cheaper, safer for miners, and less destructive to the environment. You don't have to haul millions of tons of rock to the surface. That's how most uranium is extracted in Kazakhstan. But the method only works for certain types of deposits where the ore sits in porous sandstone that a solution can filter through. After extraction, the ore needs processing. It's crushed, ground up, and also treated with acid or alkali to dissolve the uranium. What you get is a solution containing uranium, along with a bunch of other elements: iron, calcium, sulfur, rare earth elements. This solution is purified, and the uranium is precipitated as a concentrate called yellow cake. Though it's not always actually yellow, it can be greenish, brown, or black depending on the impurities. Yellow cake. That's uranium oxide with a concentration of about 80% uranium. Looks like a powder or a sintered mass. This is already a concentrated product that gets shipped to the next stage of processing. But it's still natural uranium, a mix of isotopes where uranium-238 makes up 99.2% and uranium-235 only 0.7%. And for nuclear fuel in most reactors, you need to enrich uranium-235 up to 3 to 5%. Uranium enrichment. That's a separate high-tech industry, wrapped in secrecy and international controls. First, yellow cake gets converted into gas. It's the only uranium compound that easily transitions to a gaseous state under normal conditions. Though normal conditions here means a temperature around 140 degrees Fahrenheit with a slight increase in pressure. Then, this gas is run through thousands of cascades of centrifuges or gas diffusion plants. The centrifuges spin at around 100,000 revolutions per minute, so fast that the outer edge moves at nearly the speed of sound. At this rotation speed, heavier molecules containing uranium-238 concentrate slightly more near the walls, while lighter ones with uranium-235 stay closer to the center. The difference is tiny, which is why thousands of sequential stages are needed. The entire enrichment process takes months and consumes enormous amounts of electricity. A single enrichment facility can use as much power as a medium-sized city. That's why these plants are built next to major power stations or in countries with cheap electricity. And this is where geopolitics comes in. Those same centrifuges can be used to enrich uranium, not to 5% for power plants, but to 90% and beyond for nuclear weapons. That's why the international community tightly controls who gets access to these technologies. The Atomic Energy Agency conducts inspections, verifies that countries are following agreements and not building weapons under the guise of peaceful energy. Enriched uranium gets converted back into solid form, uranium dioxide. From it, they press small cylindrical pellets roughly ½ an inch in diameter and about 2/3 of an inch long. These tiny pellets contain as much energy as half a ton of coal, or around 130 gallons of oil. Hundreds of these pellets get loaded into long metal tubes made of zirconium alloy, fuel rods, and hundreds of rods form a fuel assembly for the reactor. A single modern nuclear reactor, 1 gigawatt of power, holds about 100 tons of uranium fuel. That's enough for 3 to 4 years of operation. During that time, the reactor generates enough electricity to power a city of 1 million people for those entire years. all from 100 tons of uranium. By comparison, a coal plant with the same output burns through roughly 10 million tons of coal over that same period. But there's a dark side. Spent nuclear fuel is the most dangerous waste humanity has ever created. After 3 to 4 years inside a reactor, the fuel becomes saturated with fission products, radioactive isotopes like cesium-137, strontium-90, iodine-131, and many others. Some of them stay radioactive for thousands of years. A single fuel assembly radiates so much that it can kill a person in minutes from just a few feet away. Spent fuel is first stored in water pools right at the plant. The water cools it and shields the radiation. After a few years, once the most active isotopes have decayed a bit, the fuel can be moved to dry storage, thick-walled containers made of concrete and steel. These containers need to last hundreds of thousands of years, until radioactivity drops to safe levels. Where and how to store them that long? A question humanity still doesn't have a good answer to. Some countries reprocess spent fuel, extracting unburned uranium and newly created plutonium, which can be used again. France, the UK, Japan have such facilities. But reprocessing is expensive, complex, and creates additional risks of nuclear materials spreading. The US decided not to reprocess and to simply store spent fuel, waiting for a solution to the problem in the future. Control over the uranium fuel cycle, from mining to disposal, is a matter of national security. Countries with a complete cycle gain energy independence, but also the potential ability to build weapons. That's why the spread of these technologies is tightly controlled by international treaties. The Nuclear Non-Proliferation Treaty recognizes 5 nuclear weapon states and prohibits others from developing nuclear weapons, though it allows peaceful use of atomic energy. But reality is more complicated. India, Pakistan, North Korea built nuclear weapons without signing the treaty or by violating it. Iran is developing a uranium enrichment program, claiming it's for energy, but raising Western suspicions. Israel has nuclear weapons, though it doesn't officially acknowledge it. Uranium ore and the technologies to process it have become tools of global politics. Uranium mining also has environmental consequences. Tailings ponds, massive waste piles left after uranium extraction, contain radioactive elements, heavy metals, and chemical residues. If improperly contained, they contaminate groundwater for decades. There are stories of towns abandoned due to radiation pollution from uranium mining. For example, the city of Meilusu in Kyrgyzstan is surrounded by millions of tons of radioactive waste from the Soviet era, which still poses a danger today. But there's another side to this. Nuclear power provides roughly 10% of the world's electricity with virtually zero carbon emissions. In France, nuclear plants generate 70% of the country's electricity, giving it one of the lowest per capita carbon footprints among developed nations. In the context of the climate crisis, nuclear energy is viewed as a necessary component of the transition to a low-carbon economy. How much uranium is left on Earth? Identified reserves stand at around 6 million tons, enough for 1 to 200 years at current consumption rates. But that's only what's already been found and is economically viable to extract. Potentially available resources are far greater, including uranium in seawater. There's roughly 4 billion tons of it there, though extraction is still very expensive. Every single second, over 100 tons of new trash gets created around the world. Think about it. While you're watching this video, an entire truckload of waste appears on our planet. Where does it all end up? For years, the answer was simple: China. That's where Europe, America, and Japan shipped millions of tons of used bottles, paper, and scrap metal. But one day, China said, "That's enough." And suddenly, the world faced a garbage meltdown. But here's the mystery. Why would a country that banned importing other people's trash start searching for it just a few years later? Stick around till the end. You'll discover the secret that flipped the global recycling industry upside down. For many, many years, the entire world, Especially wealthy countries in Europe, America, and Japan got comfortable with a very convenient setup. They'd collect their trash, old plastic, paper, scrap metal, and simply ship it off to China. Massive container ships sailed across the oceans, loaded with tons of used soda bottles, old newspapers, and broken toys. China was like the world's global trash can. But not just a can. It was also a massive recycling operation. Chinese factories would take this waste, sort it, process it, and turn it into new products that they'd sell right back around the world. It was incredibly profitable for China. They got cheap raw materials and created jobs. And for other countries, it was perfect. They got rid of their garbage problem for relatively little money. Everybody was happy, right? Well, almost. But then, around 2018, China said, enough. Imagine a huge meeting of Chinese officials where the decision rang out, we're done accepting other people's trash. They called this policy, very characteristically, National Sword. It was like if your neighbor, whose garage you'd been dumping your junk in for years, suddenly said, that's it, take it all back. My garage is full and I'm sick of this. And that's when real chaos erupted. Countries that had been carelessly shipping their waste to China for years suddenly found themselves with millions of tons of garbage with nowhere to go. Picture this. Warehouses across Europe and America started filling up with mountains of plastic and paper that were supposed to sail to China, but now had no destination. It was a genuine shock to their recycling industry. What were they supposed to do with all this trash? Dump it in the Pacific Ocean? Toss it in deserts like in post-apocalyptic movies? Of course not, but the panic was massive. Some countries started burning waste in incinerators, which isn't great for the environment since it pollutes the air. Others scrambled to find new trash cans in Southeast Asia, Vietnam, Malaysia, Indonesia. But these countries quickly started pushing back too, because they didn't want to become the world's dumping grounds either. But here's where it gets really interesting. While the world frantically searched for somewhere to shove their plastic mountains, China started feeling a strange hunger. A hunger for plastic, a hunger for waste paper, a hunger for scrap metal. Seems impossible, right? A country that generates the most trash in the world suddenly experiencing a shortage of it? It's like a millionaire who suddenly went broke and is now searching for loose change under the couch cushions. The thing is, Chinese industry had gotten hooked on this imported high. Recycling plants, of which there were, to put it mildly, plenty in the Middle Kingdom, had gotten used to working with cheap, abundant, though not always quality, imported waste. Imagine a huge factory that processes tons of plastic bottles from Germany or the US every day. Its conveyor belts ran non-stop. Its workers knew their job. Its owners counted their profits. And suddenly, bam! The tap of imported raw materials got turned off. National Sword didn't just cut off imports. It left this entire massive industry without its usual food supply. Factories stood idle, capacity sat unused, and business owners pulled their hair out. But why couldn't they just switch to their own Chinese garbage? After all, there are billions of tons of it, right? That's where the devil's in the details. The problem isn't the absence of trash altogether, but the absence of quality, sorted, clean raw materials. The problem is that Chinese citizens don't know how to sort trash. Imagine this. People lived for decades, just like we used to, following the principle of everything in one bin, then off to the dump somewhere. That's the easiest way, you gotta admit. No need to think about anything. No need to separate anything. Just toss it and forget it. And this system that formed over generations, this habit that took root deeper than the oldest tree, suddenly turned out to be wrong. The Chinese government, facing these trash mountains growing faster than bamboo after rain, decided, yeah, this has to stop. We're starting to sort. But something went wrong. Sure, in big cities like Shanghai, where millions of people live in tight quarters, they started implementing mandatory waste separation. Imagine, now you don't just throw out trash, you have to divide it into 4, sometimes 5 different categories: wet waste, dry waste, recyclable waste, and hazardous waste. And all this has to be thrown out at strictly defined times, in strictly defined containers. But that's just the tip of the iceberg. First, even what gets sorted often doesn't meet the cleanliness standards required for recycling. Imagine a plastic bottle you tossed in the right container, but it was poorly washed and still had yogurt residue inside. Or a pizza box soaked with grease. Things like this, if there are too many of them, can ruin an entire batch of raw materials, making it unsuitable for recycling. Recycling plants that previously worked with more or less standardized imported plastic that had already gone through initial sorting abroad suddenly faced Chinese reality, a mixture that requires additional, expensive cleaning stages, or simply gets rejected. Second, logistics. Collecting billions of tons of trash is one thing, but collecting it in such a way that it reaches recycling plants as clean, sorted raw materials that can be economically viable to recycle, that's a completely different story. In many areas of China, especially in smaller cities and rural areas, the secondary raw material collection system is still very primitive. There, trash is still collected haphazardly, and sorting often happens right at the dump site, by hand, which hardly guarantees high quality. But there's another interesting angle here. China is a country that's constantly trying to upgrade itself, to become a leader in everything. And with trash recycling, it's the same story. After National Sword, they decided, okay, if we can't import, we'll build the world's best system ourselves. And they started building, modernizing, investing. New, modern, high-tech recycling plants appeared. They're equipped with the latest equipment, capable of processing massive volumes of secondary raw materials. But they need these raw materials. Clean, quality, preferably pre-sorted. And that's where the paradox emerges. There are plants, there's technology, there's the will to recycle, but there's not enough of the right trash. Picture a giant gleaming factory where robots work, but the conveyor belts move sluggishly because trucks haven't brought enough quality plastic. Or they brought it, but it's so contaminated that it has to be sent to the landfill instead of being recycled. It's like building a luxury restaurant with the best chefs, but having a shortage of fresh ingredients. This hunger for trash isn't just an economic problem, it's also a driver for further change. It's forcing China to accelerate reforms in waste management. The government is putting even more pressure on cities to improve their waste separation and sorting systems, educate the public, and implement fines for improper sorting. New logistics chains are being created for efficient collection and transportation of sorted secondary raw materials to recycling plants. Systems based on artificial intelligence and robotics are being developed for more accurate and efficient trash sorting. Imagine sorting robots analyzing every piece of plastic, determining its type and cleanliness. China aims not only to recycle, but also to use recycled materials in its own production, thereby closing the circular economy loop. This means that a system that previously relied on external sources of raw materials now has to completely reorient itself to internal, more finicky sources. And this trash hunger paradoxically pushes China to finally build a truly efficient and environmentally responsible waste management system. It's like a dragon that created a problem for itself just to heroically solve it later. And who knows, maybe in a few years, China will be not only the world's biggest trash producer, but also its biggest and most efficient recycler. That's the tangled but fascinating trash story from the Middle Kingdom. Every nuclear reactor on the planet has an emergency brake. Not a button, not a switch. A metal. Drop it into the core, and the chain reaction stops cold. Pull it out too slowly, and you get Chernobyl. The entire world produces just 70 tons of this metal per year. That's one railroad car. One single car, standing between controlled fission and catastrophe. 5 factories make it. Maybe 6, if you count one in China that nobody talks about openly. Fewer factories than NFL teams. And here's the thing, this same metal is sitting inside your phone right now. Billions of devices, atoms-thin layers. The metal is called hafnium, and nobody told you about it. But before hafnium ends up in a reactor or a chip, it has to be ripped from its chemical twin. That separation is one of the hardest jobs in metallurgy. Hafnium never shows up alone. Nowhere on Earth. Never has. It hides inside zirconium. Every sample of zircon mineral ever pulled from the ground has 1 to 3% hafnium baked into it. Always. No exceptions. Now pay attention to this. Zirconium and hafnium are chemical twins. Same atom size. Same valence. Same behavior in almost every reaction you throw at them. So alike that Mendeleev never spotted hafnium when he built the periodic table. It stayed hidden for over 50 years, until 1922, riding on zirconium's back like a stowaway. Think about that. An element hiding in plain sight for half a century. Separating these two costs a fortune. Not because the chemistry is exotic, because the difference between them is almost nothing. So why bother? One property. One single property where they're total opposites. And that property keeps nuclear reactors from melting down. Zirconium is transparent to neutrons. They fly straight through it like light through glass. That's why nuclear fuel rods are wrapped in zirconium. Hafnium does the exact opposite. It swallows neutrons, 600 times more than zirconium. 600. That makes hafnium the emergency brake of every nuclear reactor. Control rods, the metal plates that slide into the core to kill the chain reaction, made from hafnium. When something goes wrong, hafnium rods drop in. They absorb every neutron in their path. Reaction over. American nuclear submarines run on hafnium control rods. Compact, reliable, no second chances needed. Now here's where the money starts burning. To make nuclear-grade zirconium, every trace of hafnium must come out. To get pure hafnium, it has to be stripped from the zirconium completely. Both processes happen at the same plant. Both are brutal. Both start with sand. A specific mineral pulled from beaches in Australia and Africa. What happens next involves 100 repetitions of the same chemical trick and a column of machines taller than a 3-story building. Raw material, zircon sand. Looks ordinary. Slightly heavier than beach sand. Faint metallic shimmer. It gets processed into zirconium chloride, a powder that acts like salt with an attitude. Sucks moisture from the air so aggressively that workers handle it in climate-controlled dry rooms. The hardest part comes next. Liquid-liquid extraction. Dissolve that chloride in water. Add an organic solvent. The two liquids grab zirconium and hafnium at slightly different rates. Hafnium moves a tiny bit more into the organic layer. Zirconium stays in the water. A tiny bit. That's the problem. One pass does almost nothing, so they repeat it. 50 times. Sometimes 100. 50 separate extraction vessels chained together in a column the size of a warehouse wall. Liquid cycling back and forth for months. The electricity bill alone would make your eyes water. A single solvent leak shuts the whole line down for a week. Picture a 100-step coin sort where heads and tails are almost the same weight. That's what this machine does. And it never stops. After 100 cycles, hafnium comes out as a chloride compound. Still not metal. Turning it into metal requires temperatures that would melt most equipment. Hafnium chloride gets packed into a sealed vessel with chunks of magnesium. Temperature climbs to 1650 degrees Fahrenheit. Magnesium rips the chlorine atoms off hafnium and bonds with them. What's left behind is pure hafnium. But it comes out as a rough, grey, porous mass. They call it hafnium sponge. Looks like pumice stone someone left in a furnace. Pick it up and it feels heavier than it should. That ugly grey sponge costs over $1,000 per kilogram. More per ounce than gold at certain market points. And it's still not ready for a reactor. Only a handful of companies buy it directly. Framatome in France, Westinghouse in the US. Shipments move in sealed containers under strict tracking. Lose a batch in transit, and people in government offices start asking questions. Vacuum arc furnace. Temperature above 4,000 degrees Fahrenheit. Hafnium melts at 4,050. At that heat, it reacts violently with oxygen and nitrogen. Even a breath of air inside the furnace makes the metal brittle and useless. So the chamber is sealed, air pumped out, replaced with argon. No oxygen, no nitrogen, no room for error. First melt produces an ingot. Composition isn't uniform enough, so they melt it again. Sometimes a third time. The final ingot weighs 10 to 20 pounds. Gray, shiny, looks a bit like stainless steel. Think about what it took to get here. 1 ton of sand, 100 extraction cycles, a magnesium reduction at 1650 degrees. 3 passes through a vacuum furnace above 4,000 degrees, all for a 20-pound bar of metal. That bar still has to prove it's clean enough. In a nuclear reactor, almost pure and pure are 2 completely different things. Nuclear-grade hafnium must contain less than 1% zirconium. Zirconium isn't toxic, it just lets neutrons pass through. If a control rod has 2% instead of 1, it absorbs fewer neutrons. Under normal conditions, nobody notices. During an emergency shutdown, when every neutron counts, that extra percent could mean the rod fails to stop the reaction in time. 1%. That's the line between safe and not safe. Every ingot gets mass spectrometry analysis. Every batch comes with a chemical passport. The buyers don't take the factory's word for it. Government nuclear programs, defense contractors. They run their own tests in independent labs. Zero trust. The cost of a bad batch isn't money. It's a reactor that won't shut down when it needs to. 5 factories on Earth can meet that standard. And now a second industry is pulling on that same tiny supply. Since 2007, hafnium has had a second life. Inside microprocessors. When transistors shrank below 12 nanometers, the old insulating layer stopped working. Too thin. Current leaked straight through like water through a cracked pipe. Hafnium oxide solved that. A few atomic layers hold the charge where silicon can't. Every modern processor contains hafnium. Phones, laptops, data centers. Microscopic amounts, but across billions of devices, it adds up. A second major buyer pulling on a supply that fills 1 railroad car per year. 1 factory down for maintenance can move global prices. 2 offline at once, and both nuclear and semiconductor start making uncomfortable phone calls. There are no hafnium mines. Not one. Every gram ever produced is a byproduct of zirconium processing. If demand for zirconium drops, hafnium supply drops with it, even if demand for hafnium is going up. 2 industries fighting over a metal that only exists because someone else needed its twin. 70 tons a year. 5 factories. A supply chain so thin that losing 2 of them would send shockwaves through nuclear energy and tech at the same time. Next time you pick up your phone, remember this. Somewhere between the glass and the battery, there are atoms of a metal that doubles as a nuclear reactor's emergency brake, and there's barely enough of it to go around. Next one. A metal they pull from volcanic rock at 3,000 degrees. One country controls 90% of the supply. A pinch of metal, a few hundred grams per ton of steel. Add it, and the steel gets 30% stronger. Same weight, same thickness. But it takes a third more force to break it. That pipeline under the North Sea, the one carrying gas at thousands of pounds per square inch. Without this metal, the walls would need to be twice as thick. The project, twice as expensive. Nearly 90% of this metal comes from one country, Brazil, and most of it from one single mine. One company digs it up. One family controls that company. They've been sitting on this for over 50 years without most people ever hearing about it. The metal is called niobium, the quietest monopoly on the planet. But before niobium ends up in a bridge or a rocket engine, it starts as something that looks like ordinary dirt. What happens next involves crushing, floating, and a chemical reaction hot enough to melt through most metals. Araxá, small city in Minas Gerais, Brazil. Population around 100,000. Dusty roads, cattle ranches, a rodeo once a year. But underneath it sits the largest niobium deposit ever found. The mine belongs to CBMM, Companhia Brasileira de Metalurgia e Mineração. Private. The Moreira Salles family holds 70%, one of the wealthiest families in South America. They don't chase headlines. They just dig up most of the world's niobium and ship it out. Here's the thing. This isn't OPEC. No cartel, no politics, no sanctions. Just one company sitting on a geological freak. The pyrochlore deposit, a mineral packed with niobium, is so rich at Araxá that nobody else can compete on cost. Canada mines about 7,000 tons a year. Everyone else splits the scraps. Nobody comes close. And the ore they're pulling out of that pit doesn't look like much. Brown rock. Heavy. But inside that rock sits the element that holds modern infrastructure together. Mining starts open pit. Trucks the size of houses haul pyrochlore ore from benches cut into the hillside. Each load, about 200 tons. The ore contains 2.5% niobium pentoxide. 25 pounds of useful metal per ton of dirt. First step, crushing. The rock goes through jaw crushers, cone crushers, and ball mills until it's a fine, wet slurry. Grey, heavy. Then flotation. The slurry gets mixed with water and chemical agents. Air pumps push bubbles through the mixture. Niobium-bearing minerals grab onto those bubbles and float. Everything else sinks. Workers skim the froth. What comes out is a dark concentrate. About 60% niobium pentoxide. From 25 pounds per ton to 600. Just by letting the right particles float. That concentrate still isn't metal. Turning it into something useful takes one of the most violent chemical reactions in industrial metallurgy. Aluminothermy. Sounds academic. Looks like a war zone. Workers load the niobium concentrate into a steel vessel, packed tight with aluminum powder. Then they light it. Not with a match. With a magnesium fuse that burns at over 3,000 degrees. The aluminum rips the oxygen off the niobium. The reaction hits 4,350 degrees Fahrenheit. The whole charge turns liquid in seconds. No external furnace needed. The reaction generates its own heat. Self-sustaining. The molten mass separates. Niobium iron alloy sinks to the bottom. Aluminum oxide slag floats on top. Workers crack the vessel open and pull out a rough ingot of ferroniobium. 60 to 70% niobium, rest iron. Gray. Dense. Heavy as lead. That ingot is worth roughly $40,000 per ton, and most of it will end up inside steel. Now, why does steel need niobium at all? Because of a trick that engineers stumbled onto, and it changed an entire industry. Microalloying. Add 0.03% niobium to molten steel. 0.03%. A teaspoon of salt in a bathtub full of water. When steel cools, its crystal grains grow. Bigger grains mean weaker steel. Niobium atoms lock into the grain boundaries and stop them from growing. Smaller grains. Tighter structure. 30% stronger. Same weight. The Trans-Alaska Pipeline runs niobium steel. So do gas lines under the North Sea. So does every major bridge built in the last 40 years. And there's a reason this matters beyond construction. SpaceX uses a niobium alloy called C103 for rocket engine nozzles. The exhaust bell on the Merlin vacuum engine, niobium. It handles temperatures above 2,500 degrees Fahrenheit without deforming. Survives re-entry heat, engine thrust, and vacuum cycling. No other affordable material does all three. Put a number on it. The global market moves over 80,000 tons of niobium a year, worth roughly $3 billion. Almost all of it flowing through one company in Brazil. But ferroniobium is the commodity product. The real money starts when you need pure niobium. and purifying it requires a machine that melts metal with a beam of electrons in a sealed vacuum. Pure niobium, 99.9%, not an alloy. The element itself. Getting there means electron beam melting, a vacuum chamber. A focused beam of electrons hits the metal hard enough to push temperature past 4,400 degrees Fahrenheit. Niobium melts at 4,474. Most impurities evaporate before the niobium does. The beam sweeps back and forth, melting the bar top to bottom. Impurities leave as gas. Pure niobium collects as liquid, then solidifies. 2 passes. Sometimes 3. Each one cleans it further. The final ingot glows silver gray. Smooth. Dense. And worth 10 to 20 times more per pound than the ferroniobium alloy. That corrosion resistance is why surgeons put niobium implants inside human bodies. Your bone grows around it, and the metal just sits there. Decades. No reaction. Corrosion resistance is useful, but niobium has another property that makes it irreplaceable for the biggest machines in physics. Nothing protects this supply chain. No strategic reserve. No backup that can scale fast. Canada produces about 7,000 tons a year. Everyone else combined barely registers. If CBMM's Erixa operation shut down tomorrow, a flood, a strike, a political crisis, the world would burn through existing stockpiles in months. Steel mills would feel it first. Pipeline projects stall. Bridge construction slows. Then the specialty markets start fighting for scraps. Aerospace, medical, particle physics, all clawing at the same shrinking pile. And the strangest part? Nobody talks about it. Niobium doesn't show up on the news. Not on sanctions lists. Not weaponized. China has been prospecting for alternatives. A few junior miners in Africa claim deposits. None of them can match CBMM on cost or scale. The Moreira Salles family runs it like a utility. Stable pricing. Long-term contracts. Quiet enough that nobody bothers looking for a way out. That's the genius of it. The quietest monopoly works because it never gives anyone a reason to break it. Niobium. Named after Niobe, daughter of Tantalus in Greek mythology. Discovered in 1801, ignored for a century. Then someone figured out what a few hundred grams of it does to a ton of steel. And the metal went from a curiosity to a dependency. One mine in Brazil, nearly 90% of global supply, makes steel a third stronger with a pinch, stops particles at CERN, powers every MRI scan, survives rocket exhaust at 2,500 degrees, 80,000 tons a year. One family, no headlines. Next time you drive over a bridge, remember, somewhere in that steel, there are atoms from a hole in the ground in central Brazil. And there's only one hole that matters. Coming up, a liquid metal so dangerous that one broken thermometer can evacuate a building. And they still make thousands of tons of it every year. Right now, beneath our feet, millions of dollars in platinum, through which liquid stone flows at 2,000 degrees. This is a factory where sand transforms into fiber thinner than a human hair, and somehow comes out stronger than steel. Most people think the most valuable thing here is the giant furnace, but they're wrong. The most expensive part is the invisible chemistry, without which the entire material literally crumbles to dust in seconds. Every factory guards this recipe like a military secret. Without it, there'd be no modern yachts, no wind turbines, no airplane fuselages. Today, we're going where outsiders aren't allowed. And the strangest part, we're saving for the end. The whole process starts with a pile of sand and rocks. They use pure silica sand, limestone, and kaolin clay. We're talking massive volumes. Every single hour, they dump tens of thousands of pounds of this mixture into the furnace. For anyone searching for fiberglass manufacturing technology, understand this. It's not just melted glass. It's a strict chemical formula where every percentage point of borates or calcium determines whether your future boat falls apart in the middle of the ocean. These ingredients get mixed in giant hoppers and fed into the furnace, where absolute fiery chaos reigns. The temperature inside that furnace hits 2,500 degrees Fahrenheit. It's so hot that if you threw a chunk of scrap steel in there, it would vanish faster than you could blink. The glass becomes liquid like water and starts glowing with a blinding orange light. Right now, we're standing next to the main source of danger. This furnace runs non-stop for years. The furnace walls are made of special refractory brick that slowly dissolves into the molten glass. Imagine living in a house that you're slowly eating yourself. After 3 or 4 years, they have to rebuild the entire furnace, and that costs a fortune. But the real magic of this plant is hidden below. Underneath the furnace, they've installed plates called bushings. These are the most expensive pieces of hardware you'll ever see in any industry. Each plate is made from an alloy of platinum and rhodium. Why not steel? Because any other metal would simply dissolve in the hot glass or oxidize within hours. A single one of these parts can cost more than $200,000. The plant has hundreds of them. That means right beneath us, there are millions of dollars worth of precious metals with molten rock flowing through them. Each platinum plate has thousands of microscopic holes. When the liquid glass passes through them under pressure, it comes out in thin streams. And this is where the coolest stage begins, the pull. These streams don't just fall down. They're caught by a winding machine spinning at over 60 miles per hour. The glass is pulled so fast, it becomes 10 times thinner than a human hair before it even has time to cool. If you search online for how fiberglass is made, you've seen these shiny threads, but feeling their speed in real life, that's a whole different story. Here's a huge problem right at this stage. Thin glass is an incredibly brittle material. If these strands just touched each other, they'd instantly grind apart and turn into dust. So while the strand flies from the bushing to the spool, it needs to be lubricated. Every fiber gets coated with a special chemical solution. This is each factory's secret weapon. This solution protects the glass from self-destruction and lets it bond with epoxy resin later. Without this chemistry, fiberglass would just be a pile of useless glass garbage. Now we're watching thousands of strands gather into one thick yarn called roving. A single spool like this can weigh 40 pounds and hold tens of miles of continuous strand. Look at these rows of machines. They run around the clock, creating material for wind turbine blades, yacht hulls, and aircraft parts. The scale of production here is mind-blowing. In a single day, this factory churns out enough fiber to wrap around Earth's equator several times. A lot of people ask why fiberglass is so strong. The secret? Glass in fiber form has no microcracks like regular window glass does. It's pure molecular strength. Take a bundle of this fiber 1 inch thick, and you could lift a truck with it. But working with this stuff is a serious challenge. Glass dust is constantly floating in the air. Walk in here without protective gear, and within 5 minutes, your body starts itching like you fell into a patch of stinging nettles the size of a house. The workers here are used to it, but for a newcomer, it's a real test of endurance. Once the spools are wound, they're shipped to massive drying ovens. That's where the threads fully harden and the chemical protection bonds to the surface. Temperature inside those dryers? 280 degrees Fahrenheit. It's a long haul, 12 to 24 hours. If moisture gets trapped inside a spool, all bets are off. Mold, total loss of strength, you name it. For anyone interested in fiberglass construction, here's what matters. This material doesn't rot, doesn't rust. That's why shipbuilders love it. When you see enormous sheets of fiberglass cloth laid into molds for future vessels, you get why this factory matters. Without these thin threads, we'd still be building heavy, clunky structures out of metal that's terrified of every drop of salt water. The production cycle at this facility is a continuous flow of energy and materials. Every minute the furnace runs costs hundreds of dollars in gas alone. Now add the cost of maintaining platinum bushings and the salaries of specialists who know how to tame molten rock. This is an extremely high-stakes business. Any mistake in the glass formula will cause the strand to start breaking. If a break happens at 60 miles per hour, it creates a massive tangle of filaments that has to be cleaned up by hand, shutting down the entire line. Right now, we're passing the shop where fiberglass is chopped into small pieces 1 or 2 inches long. This chopped fiber is added to plastic to make it stronger. It's used to make parts for your cars, appliance housings, and even smartphones. When you're holding a tough plastic object, chances are there are thousands of tiny glass skeletons hiding inside it, made right here. At the end of our tour, we see the finished goods warehouse. Thousands of pallets stacked with gleaming white spools. They look absolutely peaceful, but inside each one lies the energy of a blazing furnace and the precision of precious metals. This production isn't just industry, it's the triumph of human ingenuity over raw matter. Turning sand into fabric that can withstand ocean pressure or open sea wind. That's what makes me marvel at these plants every single time. If you Google fiberglass applications in industry or fiberglass properties, you'll find thousands of pages of text, but nothing replaces that smell of hot glass and the feeling of static electricity coursing through your entire body on this factory floor. This is where the future of our infrastructure is born. I'm thrilled we got to peek inside this closed-off world. Fiberglass manufacturing remains one of the most secretive industries because every plant guards its own glass recipes and chemical coating formulas. It's a world of big money, extreme temperatures, and massive risks. But it's thanks to this insane process that we have lightweight cars, fast planes, and reliable buildings. I hope you enjoyed this walk through fire and platinum. We saw stone become spider silk and learned why it's so brutally difficult. Make sure to check out my other industrial deep dives where we break down the most fascinating factories on the planet. It was lively, it was scorching, and it was incredibly eye-opening. Thanks for taking this journey with me. See you on the next tour, where we'll find something else massive, complex, and absolutely one of a kind. Stay safe and keep away from molten glass unless you've got yourself a shiny silver heat suit. Worth mentioning here, a lot of people are curious about fiberglass for insulation or making composite materials, and this plant is the very first link in that entire chain. Every composite starts right here, at the platinum bushing beneath that blazing furnace. Without this foundation, there'd be no space rockets, no modern construction. See you in future videos, where we'll unlock the secrets of other off-limits facilities. Today, I dragged you to a place so remote that cell service seems like technology from the distant future. And the main bosses here are massive excavators with wheels big enough to comfortably fit a small studio apartment. We're starting our journey at a nickel mine. Have you ever wondered where that perfect shine on a surgeon's scalpel comes from? Or why your pot doesn't turn into a pile of rust after cooking your first batch of borscht? The answer lies here, 1,600 feet beneath our feet. Nickel. This is the guy that makes steel tough and resistant to just about everything. But finding it? That's an adventure for the patient. Look at these numbers. To extract just 1 ton of pure nickel, miners have to move and haul to the surface about 100 tons of ore. That means the useful metal content in this rock ranges from 1 to 3%. Massive underground machines load up rock that looks like ordinary gray stone, but hidden inside is the promise of future strength. One of these dump trucks carries 240 tons of rock at a time. That's the weight of roughly 40 adult elephants, if you like those kinds of comparisons. After we've brought the ore to the surface, it's got a long journey ahead to the processing plant. There, the stone gets crushed into fine sand, washed, sifted, and turned into concentrate. It's not metal yet, but it's getting close. Then this concentrate gets shipped to a metallurgical plant. And this is where things get really interesting and really hot. We're standing inside a shop where electric arc furnaces are doing their thing. Here, temperatures climb to 3,000 degrees Fahrenheit. That's roughly 10 times hotter than your home oven when you're trying to roast that holiday duck. All this molten metal churns like fiery soup, glowing so bright that without special goggles, you really shouldn't look at it. Not if you plan on seeing anything else for the rest of your life. Into the furnace goes scrap iron, that same nickel, And one more critical player: chromium. Chromium is a whole story unto itself. For steel to officially earn the right to be called stainless, it needs at least 10.5% chromium. When this metal contacts oxygen, it forms an invisible, incredibly thin oxide film on the surface. It's so thin we can't even see it, but it becomes that impenetrable barrier that keeps the iron from oxidizing. So stainless steel doesn't rust, not because it's magical, but because it's already coated with a protective layer at the atomic level. Once the steel melts, it goes through a procedure called argon-oxygen decarburization. Sounds like the title of a PhD thesis, but the idea is pretty straightforward. Surgical steel has to be incredibly pure and contain extremely little carbon. Too much carbon? It'll buddy up with the chromium, steal it away, and the steel loses its resistance to corrosion. A mixture of gases is blown through the molten metal under immense pressure, literally burning out the excess carbon while leaving all the useful additives in place. The whole process takes about 90 minutes. You can't rush this. One mistake in the proportions, and instead of a valuable medical instrument, you get ordinary rebar that'll be covered in rust spots within a few months. Next, this fiery liquid gets poured into continuous casting machines. Steel solidifies into long, massive strips that professionals call slabs. A single slab can weigh 20 tons and stretch about 40 feet long. When they come out of the machine, they're still glowing dark red, radiating so much heat you could toast bread in a fraction of a second without even getting close. Then these slabs head to the rolling mill. Picture a giant version of a rolling pin, except instead of dough, you've got a 20-ton chunk of red-hot steel, and instead of a baker's hands, you've got massive rollers pressing down on the metal with thousands of tons of force. The metal gets run through these rollers again and again, getting thinner and longer each time. From a slab 8 inches thick, steel workers produce coils of steel ribbon just a few hundredths of an inch thick. The speed at which steel flies through these rollers in the final stages hits 40 feet per second. It looks like an actual fiery arrow racing through the plant. Now let's jump to a completely different place. Gone is the hellish heat and roar. We're at a medical instrument factory. The atmosphere here feels more like an operating room or lab, sterile, quiet, and fanatically detail-oriented. That steel ribbon we saw earlier, it's cut into small blanks. Then each blank is heated again, but now in small induction furnaces and forged in special dies. That's how the rough profile of a future clamp, forceps, or scalpel emerges. After forging, the real precision work begins. Craftsmen use grinding machines and hand finishing to perfect every curve. This is absolutely critical, because a surgical instrument must be perfectly smooth. Not a single burr or microscopic pit where bacteria could hide and multiply. The tolerances here are so tight they're measured in microns. A human hair is about 50 microns thick. We're talking about precision down to 5 or 10 microns. Once the instrument takes its final shape, it goes through heat treatment. It's heated to 2000 degrees, then rapidly cooled. This makes the steel hard, so the scalpel won't dull after the first cut, and the clamp won't bend in the doctor's hands. But after hardening, the metal becomes brittle, so it's heated again slightly, a process called tempering, to restore the necessary flexibility. One of my favorite stages is passivation. This is when the finished, already shiny instruments are immersed in baths of strong nitric acid solution. You'd think, why torture a finished product? But the acid does something really useful. It dissolves any microscopic particles of regular iron that might have gotten on the surface from the machines or the craftsman's tools. This cleaning allows that same protective chromium film we talked about at the beginning to become even thicker and stronger. After this treatment, the instrument can handle thousands of sterilization cycles in autoclaves at 273 degrees Fahrenheit under 2 atmospheres of pressure and stay shiny and clean for years. Let's crunch some numbers here, because they always help us grasp the scale of what's happening. The world produces about 50 million tons of stainless steel every year. If you stretch that metal into a thin wire, you could wrap our entire planet thousands of times. But only a tiny fraction of that steel, less than 1%, gets to become a surgical instrument. To manufacture one quality operating room set, you've got to process hundreds of tons of rock, burn through thousands of kilowatt hours of electricity, and run over 30 different quality tests. For instance, one ordinary surgical clamp passes through the hands of at least 12 different specialists, from the blacksmith to the quality controller, before it lands in its packaging. Quality control here is so strict that a tool gets scrapped even for a microscopic scratch on the surface, something the naked eye wouldn't even notice without serious magnification. And here we see the final result, a tool weighing less than 2 ounces, but packed with the labor of thousands of people, from those who descended into dark mines for nickel, to those who calibrated the lasers for marking finished products. It's a long journey, where every step is a battle for quality and purity. Subscribe to the channel so you don't miss our next deep dives, because the world of manufacturing is way more fascinating than it seems at first glance. Thanks for watching, take care of yourselves, and choose only reliable tools for your life. See you in the next video. By the way, what do you think? Will humanity ever find a metal even stronger than today's steel alloys? Or have we already hit the peak of what's possible in this field? What if the metal that still powers most cars on the planet has been quietly poisoning people since the days of the Roman Empire? And we found out too late. Lead-built aqueducts adorned the faces of Egyptians, and today hides in billions of lead-acid batteries, without which cars, elevators, and entire cities would grind to a halt. We'll descend into mines where explosives shatter rock, trace the journey of galena to red-hot furnaces, and discover why this metal simultaneously saves infrastructure and destroys health. Stick around till the end. One fact about lead will forever change how you look at an ordinary battery. Okay, let's rewind the clock and dive into a story that began long before the first smartphones and even before the invention of the wheel. How did people even learn about lead, this sneaky, two-faced metal? Truth is, nobody knows exactly who or when first discovered lead, because it wasn't officially discovered by a scientist in a lab like many other elements. Lead is one of those metals that's just always been around humans, and its history is intertwined with the history of civilizations themselves. Picture this: ancient times, way before people learned to work with iron, or even copper. They were searching for interesting stones, clay, anything they could use. And then, in certain places, especially where there are ore deposits, they stumbled upon a really unusual stone. These were lead ores, most commonly galena, lead sulfide, which looks like dark gray, almost black crystals with a metallic shine, often in cubic shapes. Lead ores often lay close to the Earth's surface, and there was plenty of it around. Plus, lead sometimes occurs in its natural, pure form, though that's pretty rare. Lead has an incredibly low melting point, just 621 degrees Fahrenheit. This means you didn't need some super high-tech furnace to melt it down. A good hot campfire was enough, and if there happened to be lead ore nearby, shiny liquid metal could literally just melt right out of it. The metal in the ore heats up, melts, and starts flowing out of the rock, forming little shiny puddles or droplets. This must have been absolutely mind-blowing to witness. Out of stone, without any tools, just from fire alone, this shiny, heavy, soft material appears that you can shape with your hands. You could easily flatten it, bend it, cut it even with primitive tools. It wouldn't break like stone. This made it perfect for crafting simple objects. Archaeological findings show that lead was used as far back as 7,000 or 8,000 years ago, dating to the Neolithic period, for example, in Turkey. People found beads and other small lead objects there. In Mesopotamia, Egypt, and later in Greece and Rome, lead became widespread due to its availability and ease of working with. The Romans built their famous aqueducts and water supply systems using lead pipes. The word plumbing comes from the Latin plumbum, which means lead. Ancient Egyptians used lead sulfide for eye makeup, while Romans used it for skin lightening and in paints. Nobody back then, of course, suspected this metal was toxic. After all, lead poisoning symptoms were often chronic, developed slowly, and could easily be blamed on bad luck, other illnesses, or curses. People just saw a shiny, useful metal that was easy to work with, and they actively used it, never suspecting that beneath its appeal lurked a treacherous enemy. Now that we know the grim history of lead's discovery, let's fast forward to our time. Despite all its toxicity and the massive campaign to phase it out, lead is still part of modern industry. But how is it mined now, and where does it hide when we're so desperate to get rid of it? This is a story about precision, control, and the constant battle against its poisonous nature. Lead, like its neighbor zinc, is rarely found in its pure form. It's mostly extracted from ores, where it exists as lead sulfide, known as galena. And, as you might have already guessed, this anti-hero often shares its deposits with zinc, as well as other valuable metals like silver and copper. The world's top lead producers are China, Australia, the United States, and Peru, which once again overlaps with the geography of zinc mining. The extraction process starts with locating ore bodies. Geologists, armed with cutting-edge technology, scan the ground and conduct exploratory drilling to find spots where galena concentrations make economic sense. Once a deposit is identified, mining operations begin. This can either be an open-pit mine, where massive excavators strip away the top layers of earth, gradually working their way down to the ore, or an underground mine, where miles of tunnels are drilled, penetrating deep into the Earth's crust. In underground mines, drilling rigs are used to create holes in the rock, which are then packed with explosives. After controlled blasts that break up the ore vein, specialized loaders gather the ore fragments and haul them to the hoisting shafts. Ventilation systems run at full capacity, removing dust and pumping fresh air down into the depths. All the ore is brought to the surface, where it begins its long journey to becoming a metal ingot. After crushing, the flotation process kicks in. This is a chemical-physical method that separates different minerals. The crushed ore is mixed with water and special reagents in massive tanks. These reagents selectively attach to galena particles, making them water-repellent. Then air is pumped through the mixture, creating bubbles that the lead mineral particles cling to and rise to the surface as foam. This foam is collected, forming lead concentrate. The waste rock settles at